at least a sound check, because most folks did not log out, as I didn't either. But can somebody from the classroom make sure that you can hear us okay?
Yep, can confirm.
I hear you.
Great. Well, welcome back, everybody. Again, in the interest of staying on schedule, we will get started now. As a reminder, the next break will be at 3 p.m. Eastern Standard Time. And we're getting started. So, Jay, back to you.
All right, Jose, just give me a quick, hey, yeah, Jay, I see your slide.
We see you, and we see your slides.
Perfect. All right. Well, I hope everybody enjoyed your running around for a minute. I tried to start grading one of my exams I gave this morning. I don't know. Seems they did all right in spite of me. I don't know. But yeah, so we went through quite a bit this morning, and we're just going to pick right up kind of where we left off. We were still doing our little bit of our introduction. The great thing is that first section, talking about the overview of Module 1 and get into some of the history and importance of it, that's got a lot of information. So we're still in great shape time-wise, and still talking a little bit on the history and the important side of it. Here at the bottom of the hour, we'll transition more into some of those hydro core competences, but just kind of finishing up a bit more of the Module 1 overview and speaking to the history and importance side of it. As we were talking just before the break, looking at the way hydropower contributes to energy storage in a very big way, and also contributes to renewable energy storage and renewable energy generation in a big way, about a third in that area, about 96% or so in energy storage, and in just total generation, around 6% of all electricity is generated from hydropower. So if that were to go away, that would be a pretty big hit to our energy production. The slide here just gives a little bit more of the details and data related to hydro storage. Especially one thing that's interesting, our pump storage plant. It talks about the typical pump storage plant gives like 12 hours of generation. Batteries give around 2 hours of generation. I was out at Raccoon Mountain again just a couple of weeks ago, just visiting. I'd spent a lot of time out there, of course, during my days in the design world. But nonetheless, that plant, which is around 1,800 megawatts, can almost run 20 hours, full speed at that generation level. So, this is sort of, it's a generic number, throwing it out to look at some differences, but still, a lot of generation coming out of pump storage facilities. Our next slide here, again, just looking at the U.S., the impact of it, trying to show where different plants are. And certainly you read through this slide right here and you start saying, yeah, that makes sense. It makes sense that, Washington and California and Oregon, you think about the geography out in this part of the country, all the mountainous terrain, and of course, there's this big thing over here called the Pacific Ocean that gives a lot of moisture to these mountainous areas. And so it makes sense, of course, up there in Washington, getting a lot of drainage coming down out of Canada. So it makes sense that there's a lot of hydropower out here. But, like we show, looking at the map here, we have generation in all the places, except like we talked about earlier, a couple of places don't have it. But my question to the group here, again, we're just all scratching our heads, showing how brilliant we are. But what do you think one of our next big states are as far as this generation? Who's following Oregon? What would be let's say number 4 and 5, our next two big areas. What do you think those would be, And just shout it out, type it out, whatever you want to do. Another great place for a Mentee thing, but that just takes a lot of time, so I don't always do those. But certainly in the chat world, what do you guys give me? What do you think the fourth and fifth largest hydropower places are in the country?
Jay, you're starting to get some responses here. Not sure if you have screen, but I will read them out to you. We got Pennsylvania, Montana, New York, Idaho, Arizona, Nevada, and New York, New York again. So New York has three
Yes,
of
New
the.
York is a solid number four on the list. All right, so number five, what do we think number five is? Do people think it is the Montanas, the Idahos, the Arizonas? What are we thinking? So New York is right for number four. That sounds like we were voting in that direction. But how about that number five spot?
I am
It's like,
getting Arizona, Tennessee, Idaho, Tennessee. So Tennessee's got a couple of votes. Idaho's probably got four votes, trying to count as quickly as I
okay.
can.
There's some great options, but you'll be surprised it actually comes in Alabama. I don't know that I've heard Alabama mentioned yet.
Nope, no Alabama.
Okay, Alabama is kind of interesting. Actually, what happens is the Tennessee River comes through Tennessee and it dips into North Alabama. And in North Alabama, TVA has uh, three of their very large facilities are in the north part of Alabama, but then Southern Company has several other hydro plants. You have TVA has the Gunnersville, Wilson, and Wheeler pumps hydro storage hydro plants here in North Alabama on the Tennessee River. So a lot of generation there in Alabama. My next slide kind of breaks it down. We can take a quick look at it. You can see you got your Washington, California, Oregon, and then came in the idea of New York, and then of course Alabama. And then I heard Arizona's and Idaho's and Montana's and Tennessee's all fair game. They're all relatively close, but Alabama actually well north of 3,000 megawatts of installed capacity. A large portion of that is at the TVA's Wilson, the Wilson powerhouse has 21 generating units there. It was built. It's really quite a unique plant. It's one of the first ones that TVA that had generated power. Started with the Bureau of Reclamation. Started the initial design on that, and looking at the design drawings there. Quite interesting because you had so many people's hands in there. It was built in so many different stages. Units one through four kind of went in, and one through eight was the initial powerhouse, and he just kept adding on and adding on and adding on, because there was just so much water in the Tennessee River. That one plant, it's over Wilson is over 1,000 megawatts all by itself. So pretty good sized powerhouse for here in the southeast. I realize some of my Northwest friends, they don't think a 1,000 megawatt powerhouse is that large, and that's why you start looking at, Washington, 21,000 megawatts. That's a lot of power. And California, 10,000. That's just a lot of geography and a lot of plants. And then, of course, Oregon, a lot fewer plants in California, but still a significant amount of generation. So just giving a bit of a view of where this generation comes across the United States. And you can see clear down through, you got Pennsylvania. Pennsylvania has a lot of non-power dams currently being looked at. And I could really see Pennsylvania could crest that 1,000 megawatts if all those plants come into play. But it's certainly a place that has a lot of opportunity. I don't see it. Where is I'm trying to look, and this is something. This slide has got an inconsistency on it. We stop at 30. Alaska falls in right around here. So I'm curious. We'll need to update that, Jose. That'll be something to add. Is go back and add Alaska to. Oh no, I see what we did. This is pump storage on this side. I'm sorry. Yeah, there's we trimmed it at Alaska, and then we went to looking at pump storage. Um, Interesting where the pump storage list is. Where's North Carolina's got to be on there somewhere. Pretty. Oh, I forget those North Carolina plants. Whereas actually, I'm thinking of the Duke plants, which are really in the South Carolina side of the house. So that makes sense that you would think Duke, you'd think North Carolina, you would think North Carolina would have a lot of pump storage. You got their Bad Creek plant, but it's actually in South Carolina. I forgot about that. Anyway, just a couple of lists showing where the major um, storage and generation plants are. So really quite all over the U.S. You can see some smaller pump storage plants there. I think that's interesting. TVA actually has two pump storage plants. We call it Raccoon Mountain is really the main one. That's at 1,700 megawatts. But they actually had at the Hiawassee plant. It was one of the first pump storage. It's a traditional conventional unit at a hydro plant and run on a main river, but it can actually run in reverse. And so it's a pump storage capability, but we call it kind of a pump back configuration because it typically runs as just a conventional hydro plant. But still, some interesting concepts that are being looked at in the pump storage area, looking at our conventional hydro plants that have a high head associated with them and the ability just to pump that water back upstream. So anyway, just a quick list, looking at that a little bit. Have a video here. I'd say 50% chance of it working. Um, well, oh, okay, trying to get it to start. Let's see what happens. I'm going to turn off this guy because it doesn't always like my little laser being on. So hopefully you all can hear this.
Don't you hate it when you can't find something that's right in
Perfect,
front
Jay.
of you? That's like searching for climate solutions and overlooking hydropower. Carbon-free water power already creates a third of all renewable energy. Available 24/7. On-demand hydropower and pump storage support other renewables by providing clean energy when the wind isn't blowing and the sun sets. The answer to our climate crisis is already here. Hydropower, the solution that's right in front of you.
That's a video that NHA, via all of its members, came together and put out. Maybe you've seen it before at a hydro event, or maybe you happen to see it when you were scrolling on the Facebook world. But really helps us get a message out there to the people that may not necessarily hear about it. We did a couple of those different videos like that. They're out there in the YouTube worlds and everything else, but just trying to share a little bit more about our message. So what I want to do before we go to our next slide, Jose, is we talk about the benefits of hydropower. I've been talking about it a little bit this morning, but I just like the group to get on a little Minty world again. And we're just going to ask the basic question, what are some of the benefits of hydropower? Just, get you guys to brainstorm. We'll throw the words out there, we'll look at them, and then I'll go through just a number of slides where we end up talking a bit more about hydropower, the benefits of it. But I'd like to kick this off by doing this before we get into it. So, Jose, I'm going to turn it to you to do that little Minty thing. Maybe.
I am. There we go. Can you see
Okay.
it? Can you see my screen?
I'm playing with all my screens so I can eventually see your screen.
Yeah, I can see it.
Perfect. So there is the question. What are the potential benefits of hydropower?
Yeah, just throwing them out there. Just any different ones you can talk about, think about, and we are just going to go through them and kind of talk about them. Yeah, we'll give you guys just, a few seconds there, maybe 10, 15 seconds. That's a couple good ones I see out there, stabilizing frequency, black start capability. Yeah, somebody's brilliant out there. We'll talk about that. Yep, inductive loads. We go and play with the excitation systems. Playing as an inductive load basically allows us to help with voltage stability, allows us to put VARs on the system. We'll talk about that a little bit later on. Spinning reserves. These are all just great. Man, oh man, Jose, I don't even know why I'm talking about this. These people know everything already.
It's a great list.
Yeah, it really is some really good ones. Yeah, diversifying our power portfolio, highly reliable. Yeah, you guys are just cranking them out there. I appreciate you guys giving this some real thought. That's wonderful. See if I can get it to blow up so I can see some more of them.
Yeah, they're still coming in. We have about 10 individuals that have participated, Jay. We have a great list. LDES, for those that are wondering, long duration energy storage. So, Jay, what are your comments? What are your thoughts on this list?
Yeah, no, I tell you what, this is brilliant. You guys have got this list out there, and keep this in mind. I've got a handful of different ones we're going to go over, but you guys have certainly added to the list that I have, and I think I might add a couple of things on here. And when we talk about the benefits of hydropower, realize typically when you have hydropower at a conventional hydro plant, which is the bulk of our hydropower, you also have a dam. So when we talk about a dam and hydropower, sometimes we talk about those benefits concurrently, and that's what I might have in my list. So I'm going to go ahead back to sharing, and we will get back to our little slide deck, and we're going to talk through several of these extensively. So let me share. Let you see my giraffe I took a few years ago. One of my many trips I've been able to do in doing hydropower projects kind of around the world and most certainly in the US. Righty, let's go ahead and this guy. All right, perfect.
You're good, Jay.
Thank you. All right. Well, again, just thinking about it, and these were all on your guys' list already. Clean, renewable energy. I mean, it's just rain, right? It's just rain falling out of the sky. We'll talk about the cycle of water a little bit later on, but reliable and affordable and complementing those other energy resources we've talked about. Really, it's just such a magnifier of renewable energy, especially as we pair it up with our pumps, the storage capabilities that hydro has. So in other words, there's a lot of socioeconomic impacts. There's also, I mean, like me, I went and took my seniors out at Raccoon Mountain a few weeks ago on a tour of a hydro plant, and I took them to Raccoon Mountain, and then this past week we had a group go out to Chickamauga hydro plant. So hydro plants are pretty much everywhere, and they're very open to education groups. We can go out there and talk about so many different things from an education standpoint. The recreation side of it, I mean, you talk about recreation. I mean, let's get realistic. We all love going out to lakes, going out to our different rivers, going out hiking and biking and getting our boats out in the water and our stand-up paddle boards and our floating down or going whitewater rafting down some of these facilities. The idea of water management, thinking about floods and droughts, those are just things that hydropower helps because we have that dam there. We have the ability to release water. We have the ability to store water. A navigation, another really big one, just save thousands and thousands of dollars having that navigation ability out there along some of our big waterways, not to mention the environmental offset, by the fact that you're putting it out there on those barges vice all those trucks that going up and down the road. So, and you guys had more than I had here, and they were all a bunch of great ones. I was trying to read off a few of them that I didn't necessarily have on our list here, but really they're just hydropower has many positive impacts if we just stop and think about them. So I appreciate you guys putting your list out there. I may go and grab a couple of those before we teach this class again, be able to throw some of those into here. So an awful lot to talk about there, but we have to be honest with ourselves too, right? I mean, hydropower, it's not perfect. It's had some impacts, some issues, but again, everything has some pluses and minuses, and when the pluses far outweigh the minuses, we move forward with stuff. And looking at some soil around bank erosion becomes a bit of an issue. we say water use, water quality, though I must admit there's a lot of people that draw water from our reservoirs, which can be created. We get some water quality issues, especially in the summertime. We get some of the stagnant pools. I know here in the southeast, we get some O2 issues. Oxygen, dissolved oxygen levels can decrease at the sort of the downstream of some of our facilities. I say that as something, but we address all these issues. It's not like, hey, here's these problems and we're not doing anything about them. We actually are doing about them. In a lot of ways, we inject oxygen into water. We make fish passage as much as we can. We address that. On the recreational side of the house, we have these discharges that we'll do instead of doing generation. So again, lots of great things we do to minimize some of the impacts that we have listed here on the screen. Looking at growth, I talked about this a little earlier when we were looking at hydropower. Some of the biggest areas are pump storage, and let me get my button here pushed. Yes, pump storage is a big deal. Just tremendous number of plants being looked at. It's not cheap. You're talking about, digging a big hole, you're talking about buying a bunch of big equipment. These projects, I'm not seeing any current pump storage projects coming in for less than $1 billion. Some plants are multiples of billions. The ones that are closer to $1 billion are small plants. I say small plants, 300 megawatts in size, maybe. Your larger projects are looking over 1,000 megawatts inside. Those projects are $2 and $3 and $4 billion. So there are some challenges to make pump storage plants pencil out economically. I think we all agree they're worth a lot of money, but when you go to the banks and try to justify them, they just look at the numbers. And so it becomes challenging. And non-power dams are something else I talked about. Those are out there. I think current hydro is doing a good job advancing some projects. There may be others. I know up in Alaska, my buddy, Duff, he's got some actual new stream reach projects that they are looking at. We're adding a lot of capacity. Our runners nowadays are so much more efficient than the old runners that were initially put in, and we're able to routinely get 5, 10, 15% increase on a plant's output just having more efficient turbines. So that's a lot of what's going on the conduit side of the house. That's just some existing means that are there. The conduit there, the waterway is there, and we're just taking advantage of that water conveyance system. So a lot going on there also. And these are very, very small projects in that side of the house. What we looked at this number a little earlier, talking about, hey, how much power generation did we have out there in the hydro world? And this kind of gives you a little bit of a feel for that. So awful lot going on, a lot of upgrades to the existing fleet. We have some challenges, a lot of it on the monetary side, the licensing side. It becomes a real hurdle for us. Getting a hydro plant license, you can easily chew up 7 to 10 years of your life and wonder what happened to it. It just takes a lot of time to get some of these big projects across the line. And when the people look at opportunities, you can have a gas plant license and up and running in a fraction of the time it takes a hydro plant. Our hydro plant licensing process, it's really on par with a nuclear plant. Personally, those of us in the industry, we think that's a problem. We think that's a challenge. There's a lot of work and energy going in to addressing that. But yeah, the opportunities are certainly there. So, kind of summarizing this section, and really, we're now we're behind. Can you believe that? We've done all this chit chatting, and we're a couple of minutes behind. That's just fine. We're in good shape, though. But just, the quick summary, hydro's been around a long time. It's clean, it's renewable, I think the world of it. We have the generation side and the storage side. Went through several benefits of which you guys listed for us. And, there's just the list could be even much greater. And opportunities for growth, like I say, non-powered dams, really big. Pump storage, lots of opportunities there. And the one that we don't necessarily mention here, we'll talk about later, is the marine hydrokinetic side, or MHK. So again, that's our summary from sort of our history, the importance of it a little bit of an overview. So I hope that's given you guys a good start to your hydro knowledge. What I'd like to do now is transition and start talking about some of the hydropower core concepts. Really trying, and like Jose mentioned, and I know I mentioned too. We know some of you guys know a great deal about hydropower, and that's great. We're hoping to build upon that knowledge. And for those of you that are, not quite nuanced it yet, you're still coming up to speed. We're really hoping to share a lot with you. So this picture, I just like to point out some things in this picture as we start our discussion, because I think it has some really cool things that are worth mentioning. Of course, the first thing we're looking at is a powerhouse. This is a powerhouse. This is a tree, for those that didn't know that, but I think we all got that. All right, so behind my powerhouse, this is a bit of a switch yard. You can see it here just a little bit. The power comes out of the powerhouse via some cables, comes out here, hits this little switch yard. But what you notice is these big pipes running up the side of the mountain. Now, this right here is my penstock. This is not always the way they are. This is just this particular configuration, going back to what we talked about. Not everything's the same at all the powerhouses. You can see too, they got a little surge chamber up here. Sometimes the water's coming down the mountain. If we had to turn the valves off, turn the water off coming into the powerhouse, it creates a bit of a surge. This water is coming down, it hits my closed valve, and it wants to go somewhere. Well, we have it going back up, and it's able to go in and sort of release some of that energy into this surge chamber by having a big old hammer. And you think about what a big old hammer does. Well, it whacks something, and that whacking would be my powerhouse and the valves and the equipment that are turning that water on and off. So that's what that little surge chamber up there does for me. Ultimately, there's a reservoir up on top of here where this penstock would connect to. I just wanted to point that out in that picture while we're getting started and let you see as I start using some of these terms. You can see from a real picture what that actually is. Well, here we go. Let's start talking about what goes on at a powerhouse. There's just this energy transformation going on. We have this water that's sitting behind a dam. That water represents a potential. It just has the ability to get moving. It's what we call potential energy. It's something just sitting there. What we do in hydro world, we take that, and I'll say this 10 times, and you all will be experts by the end of our day here, but we're going to take that potential energy and we're going to convert it to kinetic energy. What we're going to do is we're going to open a valve. When we open that valve, water is going to start flowing. Once that water starts flowing, I've gone from this potential energy, I start converting it into kinetic energy. That kinetic energy, that water is now moving, and it comes along and hits my turbine. So I have this water that's back here. It starts moving now. We hold this forebay, this area behind my dam. That water starts moving through my penstock. It hits my turbine now. Now what I've done, I've got that kinetic energy. It's hitting this turbine. Now it's converting that kinetic energy into mechanical energy. That mechanical energy now starts spinning a shaft. That shaft starts coming up and it connects to my generator. Once it connects to my generator starts spinning. So now I've converted my kinetic energy into mechanical energy. The mechanics are my generator starts spinning. A particular component is spinning inside that generator called a rotor. That rotor is now spinning. That rotor is spinning inside a magnetic field, which another part of my generator is called my stator or my stationary winding. That stationary winding, it has that rotor spinning in the middle of it. I now convert that mechanical energy into electrical energy. That electrical energy is what finally makes it to our refrigerators and our computers and all else at our houses. We'll talk about that a little bit, but I'd just like to point it out real simply in this little introductory drawing to give you a feel of what we're looking at. You notice we have our water at different elevations. We call it the head water. The head, we'll talk about this difference in elevation from my upstream to my downstream. Obviously, water is running from the left-hand portion of this curve of this drawing down to the right hand. So that's just a real quick overview. We'll talk about it an awful lot over the next hour or so. I think it's how long. I think we're going to go till what time was it? 1500. So we have a little bit more time. Let's start off talking about the water cycle. It's interesting. I remember when, and I'm sure Jose does too, when Secretary Munoz, I think his name was, um, came to NHA meeting. Moniz, yes, thank you, Jose. I knew you would know it because you were, well, probably close to those folks.
Oh, yeah.
Yeah. So he came to one of our NHA meetings, I want to say 2000 and maybe 8, 9, 10, right around there.
No,
And
we're dating ourselves. Just so it's okay. It would have been 2015.
wow, okay, one of us is older, maybe me. Well, he came there, and there was this debate that was going on for quite a while between, let's just say, different people. And some people were debating whether hydropower was renewable. Well, of course, you had people like me that had been doing it for way too long, and we're like, wait a minute, how can there even be a debate about hydropower being a renewable energy source? We use water. We use water flowing down a hill. We have water that gets evaporation, goes up into the clouds from all these bodies of water. It turns into a little cloud. It goes into water vapor. That water vapor eventually goes into precipitation, falls upon the earth. This is just going on all the time. We don't start it, we don't stop it. It just happens. And it's this water cycle that happens that when it turns into water and it starts flowing downhill somewhere, we grab that water and we make electricity out of it. So I hope I've convinced you that hydropower is in fact renewable by this very simple water cycle. 2015, I would have thought it was before that, but hey, that's great. Hydrology. So when we talk about hydrology, what we're talking about is that study of water. And we always talk about the flow of water. We talk about CFS, cubic feet per second. I love this visualization. Think about a basketball. A basketball is about one cubic foot. That's what it has in it of water, a cubic foot of water. Well, you think about our hydro plants out there, they typically have multiple thousands of CFS, cubic feet per second, flowing through them. So imagine closing your little eyes and just see thousands of basketballs whipping down in front of your eyes. And you can start to imagine how much water we're actually talking about. This is a tremendous amount of water that flows through our hydro plants. That flows through our rivers. You know, we don't create this water. All we're doing is trying to control it a little bit. And you talk about the study of hydrology and trying to control a river. That's a very interesting thing we are trying to do. And it's every once in a while when we start having these floods, you realize we're not really in control. We like to think we are, but certainly, water's going to go where it's going to go. We just do our best to control it. So the thing I try to point out here is we're talking about hydropower. The key thing is you got to have water, and that's at cubic feet per second. And the next thing we'll talk about in a few minutes will be head. So let's just look at this diagram right here. Start showing a lot of different parts of a powerhouse. And I'll let you guys study this a little bit, and we will see this again. But we talk about my upper reservoir. That's the upstream. That's the higher elevation reservoir on the back of my on a dam. And this right here would be a very conventional hydropower plant. At this very conventional plant, we have trash racks because we don't want trash going into our turbines. So we control it. We have intake gates here, intake structures. We have gate mechanisms. Also, this is one flow path of water through a dam, i.e. through our generators. The other is, of course, my spillways. This is the other way over here where we get the water during a high water condition. We still want to be able to, allow that water to safely pass. And all the way over here, we have fish ladders. Fish ladders aren't at every facility. Every facility doesn't need them. Here in the Southeast, we don't have fish ladders. We have so many fish in the upstream and downstream. They're not trying to migrate from one reservoir to another. So we have our penstock again. the penstock is that mechanism to allow water to flow from my upstream to my turbine. We have my turbines inside this little penstock. A penstock, you can imagine like the Nautilus, right? Maybe you heard that term before, but looking at a little shell, your little snail, the way they're formed. And basically this area, what it tries to do is keep a constant pressure on the turbine all the way around. So we keep lowering the volume of this shape, the scroll case, as it goes around, because the water comes down this penstock into my scroll case, and it leaves that scroll case, and it's hitting the turbine, ultimately going up, spinning my generator, going up to my step-up transformers, going out to the grid. So just real quick, we're going to go a lot more in detail, but I love that drawing. Think about it. We'll see it again. So that's just our conventional hydro plant. When we talk about a pump storage plant, again, very traditional pump storage plant, we have lower reservoirs, we have upper reservoirs, and we have tunnels that connect those areas. This tunnel here being my penstock, bringing my water in, and then ultimately I have my draft tube taking this water on out to this lower reservoir. Connecting the two, of course, will be our power plant where we have the generators and all the different items there. And we have usually an elevator shaft or some shaft mechanism that gets me to the top of the mountain to get my power out on the transmission line. So anyway, just some quick things. We will go over those again. You'll see them. But while we had those up, I just wanted to take a quick time and take a look at them. Well, a key thing we do when it comes to hydrology, and this goes back to the sizing of our plants. We want to make sure our plants are properly sized for the hydrology of where they are. And what we do is we look at this minimum value of water needed to create my generation, and there's some maximum amount of water. And then we say, hey, look, this is sort of, I gotta size my powerhouse kind of between these. I say there's always some minimum amount of water. Well, is that what I want to size for? Look, I always have 5 megawatts of water available. Now, again, that would be in a CFS measurement. It also plays into the head. We'll talk about that in a moment. But what I'm saying is right now, and I say, hey, look, do I size my plant to operate at 5 megawatts, my minimum? Or do I size my plant to operate, hey, when there's this huge amount of water flow out there, and maybe I could get, 200 megawatts of generation. Well, I could get 5 megawatts all the time, or I could size it for 200 megawatts for, maybe 3 weeks out of the year. But realize if that was one big unit and it was 200 megawatts, well, once that amount of water was gone, those 2 weeks are over with, my generation for the year is over with too. So what we do, can we come up with these flow duration curves? And we use these flow duration curves to say, hey, what's the optimal amount of generation I should get from this site? And not only that, what's the optimal number of units I would want to use? Because again, you think like if you had a powerhouse and its most maximum day, it could generate 100 megawatts. But if it could do that maybe 3 months out of the year, you'd say, well, gosh, let's do the math on that. And let's say, hey, yeah, if I could generate 100 megawatts, 3 months out of the year, that'd be something I'd want to do. But maybe only half the year, I could only generate 50 megawatts. And maybe a fourth of the year, again, I could only do 25 megawatts. Well, you would think about that. You'd say, hey, look, where on this flow duration curve really makes sense? What do I want to do here? And you quickly see where I'm going with the math. Well, maybe you make a 4-unit powerhouse, and maybe each one of those units would only be 25 megawatts. And that way, when you have that maximum time out of the year, that 25% out of the year where you could run all 4 of your units, if the economics worked out, you could do it. But also during that time of the year when you could only get 25 megawatts, well, at least you could have 1 unit running, making power. So that's what we talk about, this idea of a flow duration curve. And what we do, we look at the drainage area, we look at how much time we exceed those areas, and we go back to the discussion I kind of just had with you and talking about, talking about, hey, how do I get the right number of units and the right number of megawatts select it for a site. Because what I end up looking at, I say, hey, look, I have my cubic feet per second. I see how much time of the year I exceed it. And you can see, looking at the math here, hey, I could get, wow, look, I can get 1,000 CFS 5% of the year. That's probably not where I want to size my plant. And the same thing, you can say, well, look at this. 80% of the year, 90% of the year, I can get, 100 CFS. Well, maybe that's where I should size it. But as soon as you do that, you end up giving up all this generation. So you can see we typically look at around 40%. That's a really good thumb number to think about, rule of thumb. So again, it's where we kind of look at that number and we kind of, we jockey back and forth based on the steepness of the curve, the shape of this curve, and how many cubic feet per second I can really get. Well, I know Jose talked about knowledge checks earlier on, and what I'm not aware of if we have any people that have those particular requirements. But one thing I want to do is say, hey, if you have those requirements, you've been talked to about that. But our first knowledge check for today is, what is the unit measurement used for the flow of water through a hydropower facility? So again, we talked about that. I said it, I don't know, 8 times maybe. Well, what is that unit of measurement? Go ahead, scream it out, type it out, work with me. I don't hear anybody. And Jose, to your question, I do not have a monitor to see.
No worries. So we have folks coming in as we speak. I think everybody is pretty unanimous CFS.
And CFS stands for?
I've been sworn to silence. So, there we go. Cubic feet per second by Jakob.
Yep, cubic feet per second. So that's how we measure flow. Well, like I said earlier, there's 2 key things we look at. Okay, there's a lot of things we look at, right? But basic physics says without these 2, you don't need to look at anything else. The next is the idea of head. We've got to make that water move. The only way you make water move without a pump is elevation. So we create the elevation with our dams. That's why we have these dams. They allow us to create an artificial elevation change. They also allow us to hold water back. So it's going to be this hydraulic head we talk an awful lot about. That is looking at, hey, the difference between the upstream and downstream reservoirs. The greater this head is, the higher our energy production. This can be in feet or meters, whatever you like to work with. Obviously, those of us in the engineering world, we're going to get everything into meters pretty quick because that really works out well with the calculations. And we will do that. And even our cubic feet per second would probably change that to maybe another number 2. But nonetheless, it allows us to look at these calculations. The other ideas of head, and you get it, right? These things are not perfect. This, when water flows, it has a bit of a loss associated with it. You get that. You would love it to be all this perfectly smooth flow coming through here and no resistance to it. But there is resistance, right? You have all this water, well, only so much water can flow through here. And if you move that water too fast, that creates issues for us. We'll talk about that later on, how fast we really let this water flow. But nonetheless, we have these different head conditions we talk about. You guys can see those. But really what I want you to walk away with the understanding is we've got to have a difference in elevation. The difference in elevation is called head. And when we do some basic math here in a minute, you're going to even get that a little bit more. But when we look at our basic calculation, the calculation that I come down to, it's just head times flow. You figure out your head times flow, and that gets you on path to calculate how much power you're going to be able to generate from a site. We'll come back to that in a little bit too. Again, when I look at hydrology, we have it's not like there's not a one size fits all, and it goes back to our discussion of early. It's so site specific. And so we have different equipment we use based on the different site. If we have these very low head conditions, typically low head plants have high flow. Like the Tennessee River out here. Chickamauga Dam, it's about 60 feet of elevation. That's it. Maybe on a good day, maybe it goes up a little bit higher, but nonetheless, it's going to be about 60 feet. But it's on the Tennessee River. One of those units out there, I think it has roughly 10,000 CFS flowing through it at maximum generation. It's moving a lot of water. So we have turbines that are associated with that. A lot of times with those Kaplan turbines that have the ability to change that pitch of the runner. Now again, what's happened is our elevation has become pretty fixed out on a lot of our plants nowadays. And so the Kaplans, we almost fix those, but that's another discussion. But a lot of the low heads, they have Kaplan type turbines or maybe bulb units, we call them. We get into more of the medium heads, and that's what a lot of our facilities are. And those are ones, right? We have this penstock that comes through my dams. We have it goes to my turbine. Those types of turbines, again, it's more of a Francis type unit, very popular. But and then we finally get our very high head plants, very high head plants. And again, do the math in your head. If you have really high head, you can kind of look at our little picture. We're showing, well, there's not a lot of water there, but that's okay. Because again, the calculation is head times flow. So if you have low flow, but you have high head, you're in good shape. A lot of those types of turbines are my Peltons, but they could also be a Francis. Francis goes to a pretty significant head, but I'll let my buddy Jim talk to you all about those in next month. So again, the math, and again, Jim has my mechanical engineering buddy, he's going to have a much more detailed equation what we have here. But it really, when we look at watts, all we're saying is head times flow. That's why I say head times flow. That gets you in the ballpark. Look at your turbine efficiencies. Those numbers are up in the lower to mid 90s. I mean, these turbines are super duper efficient. They don't have a lot of loss in them at all. And then we pluck in this 11.81, and all that is this constant takes into gravity, and you look at what the weight of water is. It allows you to calculate all that in just one simple number. So that is your real calculation. This gets you your raw theoretical power that's available. Now, energy production, right? Energy is just power with the time element. So now we just take power times time. A lot of times we'll go power. Well, my world, it's going to be megawatts. Here we're showing kilowatts. And down here we show kilowatt hours. A lot of times in the power industry, you're going to hear that referred to as megawatt hours. So that's how we figure out and calculate that. All right, here's my next knowledge check question for all my knowledge check people out there. What are the two factors that determine the amount of potential energy at a site? What are the two factors that determine the amount of energy at a site? All right, my buddy that's sworn to secrecy now will tell me what everybody's saying.
So people are starting to type. You want to give them a few minutes or just read the first responses that come in? Everybody's saying flow and head so far.
Flow and head, flow and head, flow and head. Yep, that's exactly what it is. I need Vanna White here to uncover these things for me or something. Yeah, your head, looking at feet or meters, and then of course my flow, cubic feet per second, cubic meters per second, ever how you'd want to do your calculation of choice. But yeah, that's what we really get into. It's just the most basic of things. Now I realize there are other little things that get factored into it. We'll talk about those. Without head and flow, you're just in trouble.
Can I ask a
No,
question?
yeah.
And can we go back to the slide where you showed the high head, medium head, and low head? I'm just curious. So in the low head, you're showing a river, in the other two, you're showing a reservoir. Is it always the case? Can we have like a river and high head at the same time? I'm thinking of the Columbia River as an example, which is it is a river flow, but at the same time, I think of it as potentially high head. I'm not sure, but this is
Yeah,
my
no,
question. Is it always
I
the
get
case
your
if you have a
question.
river?
Yeah, because what you're looking at, what you're saying is, hey, look, we don't put reservoir here, and we have reservoir here, but still behind a dam. So you are exactly right, and really where we're going with this discussion, if we look at this picture, like this could be anyone like you're talking about, and even the Chickamauga hydro plant or Fontana hydro plant. It has a huge reservoir behind it, but it is on a river, like you're talking about with the Columbia. There are several dams that have reservoirs behind them that are on a river. This gets back into the way we operate them, and we're going to talk about this a little bit later. A lot of times, these low head facilities, what they don't necessarily have is any reservoir capacity behind them. You have to maintain them at a very fixed elevation. So there's no storage there. So we call those run of river. And that's why it's kind of shown in this fashion right here. A lot of those, you can't fluctuate the elevation. All FERC is mandated that when the people got those licenses. I had a small project in India. I'll talk about that later. But anyway, yeah, to your point, rivers, this could be a river with a reservoir, and typically that is the case. It would make total sense.
Perfect. Thank you.
Sure. I'm going to buzz back over here. Bear with me. Oh, yeah. All right. Yeah, again, just wrapping up sort of our basic key components here we want to talk about, and looking at these, one thing we talk about is turbine efficiency, and that is a key part of the equation. And what we look at, it's just saying how efficient is that kinetic energy converted to mechanical energy, you know, and it goes to the clearance of the blade tips from, that scroll case. How close can we get to it? How much water seeps by? And as I was alluding to earlier, we're really doing just tremendous things here. There's companies that come out, they clean up your water passage, they get it really super smooth, and that this turbine efficiencies really starts going through the roof. The types of turbines talks about another thing in influencing that efficiency is just the type of turbine and the flow rate. The higher the flow rate, unfortunately, the higher that flow rate goes, the more resistance it has to the flow. And so you have an efficiency loss if you have super high flow rates. Again, you design appropriately. We know what it should be. So we design around it, and we pick very efficient flow rates. And then picking the proper turbine for the application. We have various turbines out there with a lot of great turbine manufacturers. So if you have a low head plant, you can have a few different options there. High head plants, you have different options there. So that really helps out with figuring out what my efficiency is going to be. When it comes to this energy conversion, like I said, we were going from that potential energy to that kinetic energy. So we're getting that kinetic energy converting us to that mechanical energy. Well, again, that's my turbine. But still, that's just part of it, right? You've got all your shafts, all your bearings, that rotor itself that's spinning. How close is the rotor to the stator? So I've got to convert this mechanical energy to electrical energy from that rotor stator combination. Again, this is a pretty low loss situation. It's you got that stator that is fractions of inches away from the stator winding. And you get into, again, for my electrical engineers in the crowd, we get that permeability of air, that resistance in that air gap between the rotor to the generator, looking at those magnetic lines of flux, trying to minimize that electrical loss there. in my stator winding. And then of course, in the stator winding itself, once I get into there, I'm going to get my electric generator. Well, then I've got to get into the generator cables that then go on out to my transformers and ultimately getting it stepped up to a high enough voltage before I get on my transmission lines so I minimize my transmission losses. So a lot going on here. And what we say is at the end of the day, my typical hydro plant can be anywhere from 80 to 95% efficient. And a lot of them are closer to this 95 if they've gone in and had recent upgrades. Now, if you work for a company, maybe you're an owner out there and your company's never upgraded your turbines from when they were put in years ago. I'd recommend calling a turbine manufacturer and saying, hey, what can you do at our plant? They'll come and help you with that. They'll be glad to come and do that with you to figure out where you are today, but where you could be if you make an investment. So again, that's just looking at the powerhouse itself, and that's pretty tremendous. Like I say, a lot of our ones that have been upgraded very close to this 95% efficiency, which is, I think, pretty impressive. Well, summarizing this part of our program, if you will, we're pretty much saying, hey, look, head and flow. That's pretty critical to what goes on at a powerhouse. We're initially building one. That's what you need to be looking at. Looking at what kind of equipment you're going to put in there. Again, look, it's pretty critical. To make sure you have the most efficient plant you can get. We look at our flow duration curves. They help the engineers, the designers figure out, hey, how many units should I have? How many megawatts should I have at this facility? How am I going to operate this facility? So a lot of cool things there that we've gone over, and I hope it's been beneficial to you to get some of those core concepts before we keep moving along in our world. So I'm going to pause there. We're a little bit ahead, a few minutes. So any questions towards our section? We're just wrapping up here. I'll pause for a moment, and Jose, if somebody types or raises hands, please let me know.
Yeah, thanks, Jay, and certainly for the folks on the call, please, if you do have any questions, I know that Jay has definitely ramped up the level of detail as we talked about earlier, from that onboarding fundamentals, and although quite simple as Jay has articulated here, the parameters that matter at scale, it's really difficult to get those 95% efficiencies if you're talking about hydrodynamics and the turbine types and so forth. But again, if you have any questions or your own curiosity, now's a great time. We have a hand raised, and let me make sure that I see who it is. It's from Julian. Go ahead, Julian.
Hi there. I was actually wondering, since the hydro fleet has a wide range of ages for the equipment, what's the pace of degradation you'd expect in the efficiency of turbines? Like, are there like heuristics you have for X% per year or X% per decade?
Yeah, no, that is a really good question. And I may actually even defer to my partner in crime here, but I know he's done a lot of these studies in a hat he used to wear. But what the issue is with turbine efficiency, especially with the older turbines, we get what we call cavitation. You get this idea of these air bubbles collapsing and building around your turbine, and they deform the turbine. The turbine is no longer smooth. The water's not able to flow over it. And so it causes this cavitation. That's a lot of the older turbines. Now, our new turbines, hey, they're made of stainless steel. We now understand cavitation a lot better. And so we're running our turbines a little better. And this comes from the guy that was, again, on a submarine. Cavitation was incredible for us. It's something we watched all the time. I was a throttleman. And so I would make the steam going to our shaft, which ultimately had our little propeller out the back of the submarine. And the last thing we wanted was cavitation, because people that didn't necessarily appreciate where we were would know that we were there. But Jose, when it comes to the actual, degradation over time, I'm sure there's studies out there that maybe the DOE had seen or been a part of. Can you share to that?
Yeah, just a couple of things to follow up, and maybe let me just piggyback on a few things that you said there, Jay. And Julian, it's a great question, and there's no real simple answer because it really depends how that machine was operated a certain period of time. If you're running the machines hard, if you're running them either by lack of experience or other considerations in the zones that they don't want to be run in, you really are going to encourage the onset of cavitation and damage and other things of that nature sooner than you would have done before, right? So there's a lot of things as I was trying to capture earlier and so forth. I'm always constantly dumbfounded, and I mean this, and I'm an engineer as well, by the way, and how good these hydrofoils are that we designed decades and decades ago. And when we look at about new technology today, we're talking about single percentages better from an apples to apples perspective. Now, we are developing, I shouldn't say but we are developing as an industry hydrofoils that are a little bit more hardened to cavitation, right? We're developing new control systems that can get us closer to the margin in operations without going into that zone that we could have done before. So there are a lot of things that have been done and are being done to get more energy while eliminating some of those concerns that Jay just alluded to, as a matter of fact. But we're talking about single percentages. It is, again, once you get cavitation and once you get that deterioration on the hydrofoil, you go down the curve really darn fast. So that's just a reality. But assuming an apple's a design from back in the day to a design today, it's really quite impressive at how close they were, I would argue, in many ways. But the DOE is, let me just go back to now what Jay said, the DOE through its labs and places like this have studied degradation of time. We assume certain percentages loss as a function of time, which are just really a way for us, when I was there, to kind of capture how the generation from a fairly uniform fleet goes down as a function of time. And of course, we use that, of course, to determine when those upgrade potentials are. So again, is it really complicated? It's a great question. It's a really complicated one for all the variables that I just alluded to.
Yeah. Thanks, Jose.
Thank you.
All right. Well, I'm going to go ahead and keep us moving on to our next
There
topic.
was one question, Jay. Sorry,
Oh,
I
I'm
failed
sorry.
to ask you by Shabazz Khan. What is the difference between gross and net head?
Well, let's just quickly run back there. Maybe I should have the mechanical engineer on the call talk about that. Oh, there we go. All right. So when we look at head, right, we have these four different types. And a lot of times what they are looking at and kind of our definitions here, this net head, it's the effective head. It represents the pressure that's available when the water's flowing. So this is really what I am concerned about. It takes into account any losses or anything else. It's telling me when I look what's available right there to my turbine itself. And so hydraulic head, it's just that pressure created by that differences in the elevation. And what we're saying this here between the intake and the project's tail water. So it's where you're measuring and what you're accounting for is what goes into these different types of heads. I think it's the mechanical engineers just trying to confuse us, the electrical guys, more than anything else.
What's an example of a loss? As if we look at the delta between gross and net, what would be an example of a loss here?
I mean, one of the biggest losses is just the fact that this water is coming in, and so it's going to create a loss. As it's flowing, I'm going to have a loss associated with flow, the shapes of things, the way the water has to turn to go around, to even make this turn right here. So a lot of times this intake structure, the size of it, the shape of it, what it looks like, any obstructions, like we have trash gates in the way, that obstructs my flow. All of those things take a little bit of energy out of the water or create a loss for the water if it could just flow freely right into my turbine. So that goes back to what Jose was talking about earlier. It's that when the design engineer starts actually doing his design, there's economic considerations to, okay, what should the penstock look like? How big of a trash rack should I have? How fast should I let that water to flow? So those are some of the examples.
Yeah, and Wesley added, friction, is a great example of a loss. Any kind of conveyance inefficiency by elbows, that's what Jay alluded to. And then once it gets to the turbine, then you have losses just, of course, in the mechanical system, gearbox. There's a lot of ways to create losses if there is, depending on the layout.
Mm-hmm. Does that help?
Yes, excellent. Thank you.
Okay. Going to figure out where I am. Perfect. All right. Well, now we're going to get into talk about our next topic for the next little while, looking at those types of hydro projects, components in them, and the modes of operation. The odds of me being done at 1500 are low, but we're gonna do our best. So one thing we point out, most of our projects are these conventional hydro plants. These are the ones you guys are used to seeing. That is the bulk of the hydro plants out there. When I say these conventional hydro plants, they have a dam, they have a reservoir behind them that, and we have that differential elevation. Glen Canyon's one of my favorite dams. If anybody's read the Emerald Mile, great book. If you've not read, if you're somebody that loves to read and you love to learn about hydropower and the Bureau of Reclamation and going in a dory boat, I highly recommend that book. If you like listening to it in your audio world, I know it's out there too. So the Emerald Mile, great hydro person book. Jose, tell me you've read it or listened to it.
I'm embarrassed to say that no, I have not, but sorry.
Okay. Okay.
Well, now it's on my list though. That's the
No,
perks of
it's
being here
just a
and being put
great.
on the spot, Jay. Thank you for that.
Yeah, no, it's just I highly recommend it. I don't know if anybody's on the call that can give me a thumbs up and say, "Oh, yeah, I read it and it's amazing." But Jose, if that happens, you'll have to let me know.
I will let you know. We should have done a poll to see how many are at fault, such as myself, versus those that are not. But we'll leave that for the next course.
Yeah, yeah, yeah. No, it's just a really great book. My son, who was always, thought his dad was crazy and everything else, and he could be accurate with that comment. I'm not saying he's not, but as he saw what I did, and I drug him around the world with me. He ended up finding that book, read it. Said, Dad, you've got to read this book. So he is a 15-year-old that brought it to my attention. Otherwise, I would have never have known about it. But anyway, it was kind of a neat father-son thing that we both share even this day, and we both have this great desire to want to go on a dory boat through the Grand Canyon because it just seemed like such an awesome thing. But I've digressed. We must get back to our topic at hand. Conventional power plants. Hey, I think I showed this to you guys already. You guys know everything here. So here we are again, our very traditional, conventional hydropower plant. So everybody was paying attention earlier, and I just know that, but I want to now make you just again imagine we're in a classroom together, and I just take my little red ball and I say, "Hey, what is this?" And somebody raises their hand and they start pointing thing out to me and say, "Oh, Jay, that's the trash rack." And I say, "Well, what do we call this up here?" And you'd say that's my upper reservoir in that area. And I say, "Well, what is this big gray looking thing that has a bunch of steps?" And well, you tell me that's a dam. So again, it's challenging in this world to get that interaction. But I just want you to look at these different things right now, and sort of as a self-test. You're your own person. But as I start looking at this guy right here, and I say, well, what's that pointing to? And of course, that's pointing to the penstock. And I come down through here and I say, hey, what's that? And that's my turbine. And this right up here points to my generator. And coming out of my generator, I have some generator cables or maybe generator bus. And I come up to a nice step up transformer. And I look over here and I have a nice fish passage. And right on the outside of that, maybe I have this might be my fish passage. So I look at it a little closer, and this would be my spillway right here. And ultimately I have my transmission line. So, just pointing these things out to you, helping you become a little bit familiar with them. We have this little control gateway. We got to have a way to turn this water off. This is not really how we turn the water off necessarily to control the unit, but if I have to do maintenance on my turbine or maintenance on somewhere inside of my scroll case or my draft, do I have to do work down here? I need a way to turn that water off, and so I can do that up here. I can get inside here. My wicket gates here, they're actually what control my flow of water that ultimately gets to my turbine, which ultimately controls how much load's going to be on my generator. But we'll talk all about that, how the governor comes into play. Well, again, I'll just throw out some terms here right now, but we'll look at them more specifically as we keep going along. But this is just a very traditional, conventional plant that hopefully many of you have been to. If you haven't, get out there. Well, we talked about those conventional plants, and earlier I've been discussing different types of units. This is one of the ones that Mr. Francis came up with. This is his design. These are for those medium to higher head type situations. All of our pump storage plants, these are the type of turbines you would expect to see there. And these are great. They can operate as a pump in one direction. They operate as a turbine to turn my generator in the other direction. A really just amazing piece of machinery there. The Kaplan, that looks like what you're all used to in the back of your boat. If I turn this sideways, that's what the back of our submarines look like. They had this a Kaplan type turbine pushing our subs through the water back in the day. And of course, then we have our Pelton turbine. A lot of these are out in California. That's where we see a lot of these used. That's some of our higher head plants. Mr. Pelton, what he ended up learning was, and it's kind of cool, you see this cup on the end of it, and you see it's like a double cup. And it really just increased the efficiencies of these things. Amazing. The way the water can come in through this cup. It's forced, it comes into the cut, hits this little divider it has between them and goes into both of those cups. And I really, just the efficiency. And you have to ask my buddy Jim about these a lot more, because again, I'm the electrical guy. But still, I want you to again realize that our conventional plants, they could have any one of these types of units at them, depending on, of course, how much elevation you have, how much head you have, and how much water flow you have available.
Jay, you have a great question, which you may be coming a little bit more in the future, but Jakob is asking which one of the three is the most common?
Yeah, that's without a doubt. It's Mr. Francis's, and just if you were to look at a pump turbine curve or a turbine curve, you'll see that the Francis is just operates over such a wider range, a wider range when it comes to head and flow. So the Francis is the most popular turbine out there. Well, this is a different type of unit. We initially showed a dam which had water right against it, and with that water right against the back of the dam, the penstock would just be an integral to your dam. And when we talk about penstock, how we would define that, it's just it's a water conveyance structure. It's a pipe. It's a pipe that moves water from point A to point B. It's a mechanism to move that water. Now, so we talk about water conveyance. In this diagram here, what you can see is we may have a dam that's located way upstream somewhere, and so it's remote. This dam is kind of remote from the powerhouse, but nonetheless, we got to get the water to the powerhouse. And it's like I know several of the dam structures in the mountains of California. This is a lot of what they have. Here in our region, our Appalachia hydro plant is this way. TVA has a handful of ones like this, that the dam is located somewhere, and then we have this water conveyance. That could be by a tunnel, a pipe, as you see here, open canal, many different ways to get that water So this is all at the elevation of the upper reservoir. Okay, it's not exactly at the same elevation. It has a little bit of a downward bubble to it to get the water here. So anyway, so this water moves through this conveyance, and we'll have an upstream ponding condition right upstream of our dam, and we'll have that a penstock that connects my water now that I let move through a tunnel or a pipe or whatever else. Then it gets to my powerhouse. A lot of the same things, we'll still have a dam, we'll still have a powerhouse, we'll still have a generator inside there, we'll still have a turbine inside of there. We still need that penstock. We'll have this floor base, sometimes they call it. And what's neat here, we're kind of showing, hey, look, there's a way to get your little canoe, carrying it around, and you can go a little picnic here at a lot of these facilities. Because a lot of our hydro plants, we have a lot of recreation, a lot of camping that occurs there. So again, as I transition to my next diagram, you can actually start to see what we're calling a lot of these same structures, same things, and you get it, right? This bypass reach, sometimes that has a very minimal amount of water in it. And a lot of your water flows when it comes to the powerhouse. We'll just be storing it up here. This reservoir will be this filling up, waiting for this guy to get called, this powerhouse getting called into operation so we can do it. And then sometimes we'll have spillways up here. Sometimes we'll have maybe some flow control mechanism so we can actually start, letting water flow through here. This, again, at our TVA side of the house, on our Ocoee powerhouse, we have a lot of this going on. We have actual a flume. It's right on the side. It goes for several miles. You can see it through the woods along the river. Actually, an old wooden flume that carries the water. And we have a little gate right here. And the gate opens, the water goes in, we do our generation. What we do is when it's time for whitewater season, we'll actually close that valve. The water goes over this divergent dam. It's the way it was designed. The water goes over the dam, and we have this long section for people to go whitewater canoeing. I share that because it really leads us into our next discussions when we talk about these conventional hydro plants. We have two basic types. And it goes what we were talking earlier with our question about, hey, does it have a reservoir behind it? And that's kind of a tricky question because it goes into how do you define a reservoir? What is a reservoir? Is it a reservoir or is it a river? When it's a run of river, which what we mean by that is, hey, when it rains, there's X number of water that's flowing into that river system. Well, we've got to get that same amount of water out of it. I was talking earlier, I did a project up in Indiana, and the control system there was all based on elevation. Their permit was really tight on what the upper reservoir's elevation had to be maintained at. It couldn't go high and it couldn't go low because there was a bunch of homeowners on this river that they wanted that thing at a certain elevation, and everybody was good with it. So when the rains come in, these units would get turned on, and we would, depending on how much water was coming in, a lot of projections and stuff we would do, but nonetheless, we would operate that river within a very small band. I'm talking like less than a foot, and we would have the units coming on. So basically, just what goes in goes right back out very rapidly, and that's what we refer to as run of river. And we say it doesn't have any storage behind it, which in our mind has no reservoir. It's just a river with a dam on it. Well, the other type are more conventional systems too, is the idea of a peaking, right? It actually has a reservoir behind it. It has storage capability. So since it has storage capability, we can fluctuate the elevation of that dam quite a bit. I don't know if any of you ever been like Norris Dam up in Northeast Tennessee. That place is crazy. It just several feet. I'm talking hundreds of feet in elevation. Same thing. The Cherokee dams, Norris dams, Douglas, all three of those reservoirs, they can go down. Sometimes they'll be so low that it looks like there is just a river through a little canyon. It's and so that's where we get this idea of peaking. It has a reservoir behind it. It has the ability to hold a lot of water based on the time of year. And you can show what they're showing here. This thing's just going up and down, up and down. And during those peak hours of the day, when we need lots of electricity, that's when these dams will operate. So that's kind of the difference in those two different modes of operation. So it leads me to our next knowledge check. What are the two primary modes of operation for a conventional hydropower plant? Again, so those two different, we just went over them, and I realize it may be somewhat repetitious, but again, what are those two types? I don't know if anybody's typing away, my friend.
Yep, they're
Otherwise,
typing, so giving folks a few minutes
Yeah,
here, Jay. So we got 2 so far. We got 3. So you have some differences, but I think you got run of river by everybody, and then you have peaking power versus storage. Run of river and peaking seems to be the most common response that you're getting here from the chat.
Yeah, thank you. And that's exactly what they are, right? It's our peaking is what we just talked about. And that's when I actually have a reservoir behind the plant. I can store that energy. I can store that water for usage when I want it. And of course, the run of river when I have no storage at all. All I can do is just pass the water as it comes to me. We'll talk about this. This run of river really gets kind of neat if you have multiple dams on a river. They very much in the operations side of the house, you're trying to move water from one plant to the next plant to the next plant, doing it very controlled, very systematically. Pretty cool. Now I'm gonna really make everybody scratch their heads. What are the three primary types of turbines? The three primary types of turbines we talked about. Again, I'll give you guys a few minutes typing away. I can hear you.
They're typing. They're typing.
Oh, yeah.
And we're getting convergence. Everybody's saying it. Francis, Kaplan, and Pelton.
Great. Well, and that is exactly it. My Francis, my Peltons, my Kaplans. Those are the three primary types. And again, as the next course, when we get into more of the equipment side, this is certainly more of a mechanical thing. My buddy Jim will talk about those a good bit more. Well, the next thing I want to talk about is pump storage plants. And these are just my absolute favorite. I was really blessed in my time at TVA. I started working in the early 90s, and TVA was just kickstarting their hydro modernization projects, where we were going in, putting, new governors and excitation systems and new turbines and just all kinds of upgrades to their systems. Well, in the late 90s, early 2000s, we did that at our Raccoon Mountain facility. And by that time, I learned a little bit, and I was our lead electrical engineer for that project. So I spent several years out at Raccoon, really got highly engaged in the pump storage world. And again, just really neat. What we're showing here, we have two basic types, and though I heard comments about these, and I'll leave those alone, but this idea of open loop pump storage, and all it is, you have a reservoir, typically man-made on top of a mountain, and it connects to a body of water, typically a river. Here in town, we have Raccoon Mountain, man-made lake on top. The lower reservoir is the Tennessee River. It's actually Nickajack Reservoir. But nonetheless, it's a large body of water, and all day long it's pumping up and receiving water as it goes back and forth, And the big thing is typically when we have excess generation on the system, we're in the pumping mode. And you can get it. If you have excess generation, typically the value of that generation is a little bit less. So you get this delta in the price. And so when we need electricity, obviously the pump storage plant goes in the other direction and we start generating, the water's coming down the mountain. In this scenario here, we go back into a river. This closed loop is deemed to be more environmentally friendly, and you can actually have two man-made lakes, and you can bypass some of the regulatory and permitting process. I'll not comment to that. I think both of these are great solutions. This is what we have everywhere. I don't think we have any closed loop pump storage systems that I am aware of. Typically, they're all on a body of water going up to a reservoir. So those are these two different types.
Certainly in the U.S. Global.
Certainly in the U.S.
Yeah.
Yes, and that's maybe what we're talking about here today. But there are, like I say, other places. I'll not comment to that, but I've looked at ones that connect to the ocean, and that is a different beast in itself. But I just want to get these two generic ones out there on the table. And speaking of pump storage, and everywhere I was my group of seniors about 2 weeks ago. Went out to Raccoon. You can see we're up here on the top of the mountain, kind of overlooking the reservoir, checking everything out. And then TVA was so gracious to let my students go through, get to see the whole plant. So really a great experience for all of them to get out and see a lot of this stuff we talk about in the theoretical world. And it's great that so many of you have been out to plants. I encourage you to keep going anytime you get an opportunity. I know every time I go, there's just something cool, and getting to take a group of young men like this out was really quite rewarding. So let's talk about pump storage. You start looking at it. Well, one thing you instantly see that translates to a traditional conventional pump, a conventional hydro plant. What would you think as you look at this? What do you see that you say, oh yeah, we see that exact same thing when I look at a conventional hydropower facility? What jumps off the screen at anybody? They're typing, they're talking, they're thinking. Anybody
There's
going
two paths for water.
say again?
I made a mistake. Sorry.
I'm sorry, Jose. I did not hear that person. Did you?
There was a comment, but I believe he just pulled it back.
Okay. What I would point out, and it's obvious to me, and as soon as I tell you what it is, you'll say, "Oh yeah, that's obvious." It's quite simply there is a large elevation change here between this lower reservoir and the upper reservoir. That's still the basic thing we have to rely on. Typically, pump storage plants greater than 600 feet is a really good number. Most of them have an elevation change closer to 1,000. And it just gets into the economics, right? The calculation is the same. It's head and flow to figure out how much power you can get. And so if you can get this body of water, i.e. your flow, really high up in the air, you can get more power out of that through your powerhouse. So that's the calculation. That's what we're always looking at, because you're having to dig this big hole up here. How much civil work can you afford to do? And that helps with the sizing of the powerhouse. How long of duration do you want it to run? That's a lot of the things that we end up having to figure out. But much like our plant, we have a powerhouse that's down here, typically inside the mountain. There are some that the powerhouse resides over here. It goes back to the geography. Sometimes you can have it lay right at the edge. Depends on how steep this escarpment is. If it's some long meandering mountain, it just makes a lot more sense to do it inside the mountain, where you can go straight down, straight over, boom, shoot the water out. But we have these elevators. Inside the elevators, you'll have the cables that connect from your generator, which goes to a transformer, which goes to these cables, which goes up to the top of the mountain. Again, this being my upper reservoir, this being my intake structure, as you can see, a Raccoon, this tunnel, it's 30 feet in diameter. So this is not a small tunnel at all going to the tops of these mountains. 30 feet is not unreasonable. And next down, as we get closer to the units, that makes sense. But you have your powerhouse, and then you have your discharge structure, you have your surge chambers here, right? So if we stop this unit, you want that water to have somewhere to go to. And then we have some other equipment, inside of the various chambers. So that's just kind of looking at my pump storage facility. One thing I would mention, I'm going to go to this next drawing right here. One thing that people that maybe aren't too familiar with it, when we built these, there is one generator slash motor with a three-phase motor, and that's what we're all operating on. It's all three-phase. What you end up doing is you have that one motor slash generator. You can go then swap any two phases in a motor like that. And by swapping two phases, it rotates in the opposite direction. Once it operates in the opposite direction, you basically made a turbine become a motor. The turbine is when the water's flowing out, going out to the reservoir. We're using it in the turbine mode and the generation mode, if you will. And then we swap those two cables. We swap those two phases. Now we're going to be moving water from the lower reservoir through my now operating as a pump going up to the top of the mountain. It's interesting what we actually call that switch. If you thought about it for 1 second, you could guess the name. It's called the phase reversing switch. Very complicated, I know. So we have that allows us to operate this thing in both the direction. And again, you can see by looking on here, all the different names and everything. We actually have, this access hatch, this access tunnel. It gives us the way to drive vehicles in, bringing all the equipment down in here. Our transformers, our generator breakers are all down inside of there. At a lot of these plants, they'll have the transformer inside. They'll go ahead and generate in the 20,000 volt range, and it will step it up to maybe 161,000 volt range, take it to the top of our mountain. And because these things are such large facilities, many times it'll get stepped up to the multi-100,000 volt range, sometimes up to 500,000 volts in my switch yard at the tops of my mountain. So again, just some different thoughts there. Like I was talking about, we have these two modes of operation, right? We have it operating in the off-peak, where my electricity is at a lower cost typically. And so that's when I'm pumping. You see my pumping mode going up the hill. And then we get into my when I want to generate is during these peak hours of the day when electricity costs are typically higher, or my demand starts increasing. You could have a trip out on the system somewhere. You could have you have a big fault at a larger plant, and they need this power very rapidly, because a pump storage plant can actually come online in literally minutes, can be up to full generation mode. And then that generation mode, obviously I'm talking about the water's coming down the mountain through my powerhouse and out to my reservoir. So that's those two basic modes of operation, in the pumping mode or my generating mode. So I had my next knowledge check for you, talking about what is the difference between a closed loop pump storage plant and an open loop plant. So what's that difference between a closed loop and an open loop? And this one would be tough for, I think, you to type, as a few more words involved. Though I want you to think about it in your mind, and I think you could rattle it off if you were just to say it out loud. But that basic difference comes into being is we have our closed loop is, hey, look, we're connected to we are not connected to an external body of water. Typically, in the closed loop system, these are both man-made reservoirs, and you're just pumping the water between the two. And on the open loop system, we typically have a natural body as my lower reservoir, and the upper reservoir would be more of a man-made system. So that's the differences between those two.
And we had two folks type in very much what you said. Pretty simple. I think captures. I think one alluded to open is tied to a natural source of water. Simple.
Yeah.
Correct. And and similarly, another one says draws from a flowing body of water versus an isolated bodies of water. So I think those are both, of course, correct. So So Jay, I think the team is definitely, harnessing all the information you're sending us very well. Just as a time check, we are about 10 minutes from break.
Yeah, and that's kind of a bonus, kind of a bonus. The last area I want to talk about, we've talked about our conventional systems, and there's a lot to talk about in the conventional systems. And we're talking about pump storage, and there's a great deal to talk about pump storage. Obviously, I'm very excited about that. The last area we lightly touch on, and we lightly touch on it because there is so much going on in the R&D side of the house. There are a few systems in the marine hydrokinetics, we call it the MHK system, but that are in operation. They're putting kilowatts on the system. But this is a very new area that there's not this large body to talk about here today. But we want you to be aware of it. We want you to know that, look, if we go and look at all the tidal energy and all the wave energy out there, there is tremendous opportunity. You do those calculations that talk about the theoretical potential. It's a very large number, but we just haven't got there yet. But you guys go to the beach, you see the waves. I know out west, I think is it Oregon, Jose, where we have the test facility. I think is it operational now, or it's almost operational?
Yeah, it's in Oregon, and they have a few tie-in bays. Yep.
Yeah, so there's just a lot going on here, and I just stay close to it. A lot of research going in. The Department of Energy over the last several years has funded a lot of really cool things, but like I said, you're talking about putting moving mechanical systems in the ocean, high current conditions, lots of movement, making electricity, getting that on shore ultimately, and it's just not easy. And if it were easy, well, kids would be doing it, right? So kids aren't doing this. We got grown women, grown men, very smart grown men and women doing this, and it's going to be really exciting to watch where this goes in the future. So that's really all we're going to say about MHK today, but it certainly has a lot of potential, and we're just going to just see where the future leads, see where those brilliant young men and women that are doing all the R&D right now, what they can do for us.
Yeah, and Jay, just quick pause here. Kelly, who of course is on the NHA staff, just posted on the chat for folks to see the link to the efforts that NHA is, of course, collaborating with and communicating on the MHK space. Just want to create that awareness.
Thank you, Kelly. Appreciate you doing that. Like I say, it's in the NHA world. We have a whole group there that we're supported. DOE supporting it. Some Rents, a good friend of mine out is living in and breathing this every day. So there's an awful lot going on in the U.S. in this realm, and like I say, I'm just excited to see what they sort out in time. So in a quick summary here, we've talked about these three different types of power plants: the conventional, the pump storage, the MHK. In the conventional side, we talk about the run of rivers. We talk about our peaking plants, the storage modes too. Pump storage, I can't talk enough good things about it. It's just a force multiplier. It's what's going to allow renewable energy to continue to do the great things that is happening there. And on the MHK side of the house, again, it is a future that has a lot of development going on, and it's going to be exciting to see what that group continues to come up with. Well, with that, Jose, I am done with this section, and what I would recommend we do, because going on my electrical power right now, I would just get fired up and you would shut me down. So I would just rather go ahead and start our break here 5 minutes early.
Yes, and before we do, I think it's a perfect stop from a teaching perspective. Maybe I'll just ask the team so we can, because we are going to switch gears, ask everybody, are there any questions on what I would call more of the mechanical, the governance of hydro, how decisions on sizing, number of units, everything that Jay just covered, types, pump storage versus conventional versus little bit on marine hydrokinetics. Are there any comments or questions for Jay?
Or Jose.
All right.
No
Well,
question.
yeah, please.
No question, but I want to say that was a really enjoyable module. I'm not an engineer or anything. I'm an economist, but like for me, this was like really, really great intro to Hydro.
Well, thank you for the feedback.
For sure.
Any
Any other
other-
questions? Like I say, Jose has mentioned, we have a few minutes on, and again, I'm not dying to go out on a break or anything else, but so if there's questions, let's make good use of this time. Or we can all go and maybe grab lunch, whatever you need to do. But certainly other comments or questions.
All right. Well, I don't think anybody's typing, Jay, or anybody's, of course, commenting. I'm sure folks are ready for their break. It is 2:55. So we will start. I'm going to give folks a little bit of extra time, Jay, or do you want to get the time back in the 5 minutes?
I want to be sensitive. People may have had something scheduled or whatever else. I want to make sure they have every minute of that. So I think 3:30 is going to be just
All
great.
righty.
So
Well,
we can be sensitive.
3:30 it is Eastern Standard Time. See everybody back in about 33 and a half minutes.
All right.
Bye-bye.
Take care, everyone. Great.
Hey Jay, welcome back.
Welcome, welcome, my friend.
I'm hoping that you're going to start us out with which facility are we looking at now?
Oh, no,
All right.
that'd be too easy.
It's an angle that some will know, I assume. All right, well, welcome back, everybody. We'll be starting in about 30 seconds. Just can somebody do a check from the team, make sure that everything is a go? Perfect. All right, Jay, it is 3:30.
Yeah, it's 3:30 and I am going to sort this out. You're going to forgive me. Do. All right, there we go. Man, first world problems. Well, welcome back, everyone. Jose wanted me to ask, what plant are we looking at in this picture to see if we have any brilliant hydro enthusiasts amongst us?
See if folks are anybody willing to either type or just come on the mic. No responses yet, Jay. Maybe it was a tougher than you thought it was.
Do what?
I said no responses yet. Maybe it was tougher. There's one by Dylan. Wesley with a question mark. Um, in the interest of just keeping it on time, Dylan, you're correct, and Wesley, your question mark could be removed. Hoover Dam. Filled with
Yeah,
water. It doesn't always
it,
look like this.
and it is an interesting view, no doubt. You're so used to seeing it from the downstream, and clearly this is not the downstream view. We are in the reservoir, if you will. All right, well, folks, I hope everybody had a nice little whatever you need to go do. You know, I personally had lunch, and it was amazing. So over the next, what do we have? An hour and a half, and we have got some great stuff to talk about. We're going to go on the electrical system. This is kind of the first part of what would be the electrical the equipment lecture for module 2. I kind of take over this. It gives my buddy Jim a lot more time to talk about all the mechanical and civil equipment, and also he just felt more comfortable, and obviously I felt comfortable talking about this. So this is, we're going to transition and talk a little bit about the electrical overview, and then we'll come back, talk about just a typical river layout. I'll go through the TVA system and look at it with you, where we can see where we have conventional plants, the run of river, the reservoir type places, looking at pump storage, and then go through some slides too, the new slide deck of another system, and maybe share a little bit about that as our time allows. But a good bit of the next hour or so will be just going through the electrical piece of it, really focus on the electrical generation a little bit, and ultimately what it looks like when we tie to the grid. We'll talk a little bit of electrical engineering. I think everyone will be fine. We'll keep it at basic Ohm's law, maybe throw out a little bit of Mr. Faraday and Mr. Maxwell. Mention heavy side just because I think the world of him. The guy's beyond brilliant, as a total recluse that he was. Any electrical engineers in the group may recognize that name. Mechanicals should recognize that name, but maybe not. Anyway, we'll just jump right in talking about our electrical stuff. Again, as we shared before, raise your hand and virtually interrupt me, ask questions, because you're not going to be interrupting me. So just really encourage the dialogue, and I appreciate all that we've done so far today, and you guys encouraging me in this very digital/remote lecture that we're going through. So let's talk about electrical stuff. We start off inside. This is a view of obviously the inside of a powerhouse. You look through here, some neat things. I always like looking at the pictures and say, hey, what's in that picture? What do we see there? As I look through this one thing, a nice lifting beam over here for moving stuff in and out of the generator. That's always a cool thing for any civil engineers in the group. Now, obviously, we're looking at the top of the generator housing. You can see this little line coming over. My thought is that could be the oil lines for the hydraulic system. That would be my guess. Up here at the top, we have our pilot exciter device. That could be a cable going over to the pilot excitation system. If anybody knows this plant, feel free to mention what that is, but it definitely looks like hydraulic oil coming over, and this being potentially a a Kaplan unit, that being my oil supply coming over from my governor. Anyway, you can see we got what inside of here. We have my excitation system. Be able to brushes inside of here. Brush rigging basically allows for the voltage control. Voltage control really means excitation control means voltage control means VAR, volt ampere reactive control, and we'll talk a little bit about that. But the big thing I want to mention as we get started here, we're now at the last step of our energy production, and we've talked about this transformation of energy all through the process. So instead of me rambling it out, I want to say, hey, I'm ready for my next knowledge check to you guys. As we convert this water power to electric power, what are the stages of energy we go through? We've mentioned this a few times, but it's probably about 5 different types. You guys will get 4 of it really easily. I'm going to be impressed if somebody comes up with a 5th. And it's probably me reaching a little bit, but that's okay. So again, this is those steps of energy that we're going through as we go through this process. What is it? I'm hoping somebody's at least typing away. I'm gonna give a few seconds. I'm gonna ramble. I'll just talk here for a quick second while you're thinking about those energies. That first one we talked about, that water storing up behind the dam, and then the water got moving and it made other things move, and as it was moving, it created something that eventually led to something going out on transmission lines. So all right, Jose, how many people have I got mentioning
We
4 or 5
have
things
so
here?
far 4 respondents. Let's give folks another 15 seconds. We have a lot of good answers, and some folks are actually agreeing by thumbs up to others. So
Good.
there's one individual who took a stab at the 5. So I'm going to go with that one as I'm going to verbalize it.
Okay.
Potential to kinetic to mechanical to magnetic to electrical.
Brilliant.
That was the 5, the only one with 5. We have others with 4 and 3s, and be glad to share those if you like.
Yeah, no, I had not mentioned magnetic yet. I maybe alluded to it a little bit, but I'm really excited for the brilliant individual, whomever that was, probably a civil engineer or something. I don't know, maybe mechanical, maybe an electrical. Anyway, we're going to talk a lot about really the magnetic and electric part of the process. We've talked an awful lot thus far, that potential to the kinetic, to the magnetic, to the mechanic. And finally, that mechanic is really, it gets that rotor, that rotating magnetic field rotating, right? And we can do that many different ways. We're talking electric, we're talking hydro here specific today, but as far as the generator goes, a generator doesn't really care what the prime mover is. Our prime mover today is water going against a turbine moving it. We could have steam, we could have gas, we could have steam being from a nuke plant, a coal plant, whatever. We've got to get that motion, that relative motion between the rotating field and, i.e., the rotor, and the stationary field, the stator winding. So then that's where we get the idea of the magnetic, which I've not really talked a lot about yet. And then finally, as those magnetic fields create, and that's where we have all those brilliant people, Faraday for sure, Maxwell for sure, showing that relationship between magnetic to ultimately electric. The magnetic field intensity and of course my intensity of my electric and the current. Ultimately, magnetic gets the current flowing. So we'll talk more about that as we get going. Well, the first piece of equipment I want to talk about is the governor. And this is not the guy that sits in the capital of your state and tells people what to do and does things good or does things bad, depending on how you view it. The governor for us, it is the primary mechanism that controls the position of the wicket gates. The wicket gates, think of them as a valve. These wicket gates, they control how much water is let into our turbine. And so depending on how much water goes into our turbine, that controls how much kilowatts we put on the system. It's kind of interesting, and realize our generators, the governor, it's thought of as a speed control device also. But what ends up happening once once our unit gets tied to the electric grid, we go through, we parallel, and I'll talk about that later. We parallel across our generator breaker. We synchronize all of our ABC phases are totally in phase with what's going on out in the electric system. Well, the grid is so big, it dictates what speed your unit's going to turn at, namely 60 hertz. Whatever speed it was going before it got online, whatever frequency it was operating at before it got online, as soon as it ties into the system, it is at 60 hertz. The system demands that, and the speed may slow down a little bit, or it may have picked up a little bit, depending what goes on. And it's that speeding up or that slowing down, that's where the kilowatt load comes into play. Think of it as like you and, okay, I got a brother. He was always little than me, hence I refer to him as my little brother. So we would have to go, he and I have to go work sometimes. And let's say he and I, we both had to push start our car. It was during the days of clutches. Some of you with hair that looks like mine understand what I mean. We would have this car and we would have to push the car to get it rolling. Well, we were both of our hands would be on the back of the car, and we're both pushing. We're both going at the same speed, right? We're both touching the car. But he was my little brother. I was pushing as the same speed he was, but I was pushing harder. I was doing more work. If we could have measured my wattage output, my wattage output would have been more because I could put more force and more pressure into it, though our speed was the same. So that's the thing we talk about a governor. A governor, when you're offline, when you're not tied to the grid, it's strictly speed control. You don't want your unit running away from you, getting away from you, overspeeding while you're getting it ready to load to the system. But once you get it online, all you're doing at that point is varying how much megawatt load, how much work are you really going to put into it. So keep that in mind. A governor is a load control, a kilowatt controlling device. In a little bit, we're going to talk about excitation, and it talks about more the reactive, the imaginary power. But this is that real power, that real work that a hydro unit puts out. It's controlled. The governor controls the water, which ultimately controls how much work the unit can do, how much real wattage it can take on. Now, when we talk about our different dams, there's a lot of different things out there. But today, I'll keep it at some of the more major parts. We're going to talk about the generator. We'll talk about the transformers. We'll talk about the breakers a little bit. We'll get into control systems a little bit, some of the aux power stuff inside. Jim will talk a little bit more about a lot of things. But, a lot of this is made on IEEE. That's our governing body on the electrical engineering world. NFPA, National Fire Protection Electric Code, NFPA 70. Some of you folks may have heard that. The National Electric Code, we get into that too. NFPA 101, fire protection. So there's a lot of these different codes go into a powerhouse. Now, these entities, especially like the National Electric Code, Now, a lot of times we say, hey, it's inside our powerhouse. We are the jurisdiction, having authority. We can do what we want. Well, we want to do it right. And the National Electric Code has a bunch of great lessons learned. So these are some of the documents we use when we go into designing a power plant and or modifying them for sure. Well, let's talk about electricity, right? Now, earlier I sometimes joke and I talk about how we get the electrons out of the water and put them out on the grid. But in reality, like we've talked about, it's all about this motion. It's all about this magnetic flux we get created as we get spinning our units. Well, all of our units generate three-phase power, ABC. Much like you coming into your house, most of your houses have two phase that come to your house, but you're operating on single phase. We're operating between those two phases and phase to ground. We get that 120 volts. Well, we generate this 120 degrees apart. Typically, our hydro generators at the more the conventional plants, they're generating around 13,000. The pump storage plants and the larger hydro plants, they'll be around that 20,000 volts range. When we talk about this volts, that's just those electrons. We're getting electrons to move. They have to have that potential of difference, that voltage behind them to cause it to move. The other key thing we talk about is resistance. Resistance is just that opposition. It talked about that of the electrons. It's how we measure the actual resistance. Our goal in designing stuff is to make sure we size our cables, we size our transmission lines, so as when we study them, we can say, hey, it's essentially zero resistance. Now, hey, it has resistance. You get that, but we size it so it appears it has zero resistance. Then if we overload it a little bit, that's fine. We got some wonderful margin in there. In our plants, we have AC systems and we have DC systems. What's great nowadays, we have preferred AC systems, right? That feed off things. We have those UPSs, uninterruptible power sources we put inside our power plants. In our power plants, we have very large batteries in the event that we become an island, we trip offline, there's a big storm that comes through. We want our control systems to be able to operate. We talked about black start capability earlier as one of those cool things that hydro can do. It can do that provided it has a battery there to provide some of the initial controls to get the units online. Once we get it up and generating, again, we can start paralleling outside of the plant. And when I say paralleling, what I mean is connecting our generating station to the grid. And we parallel, and why we use that word is this we have these three phases, A, B, and C phase. Well, everything has to be in phase. The voltage that we're generating, we have to get it exactly in phase with the system we're connecting to. Do we have meters that the operators can look at to do that? Or nowadays we have, auto paralleling equipment that can actually auto synchronization equipment, we call it, that can allow us to actually connect our system totally automatically. The old computer just says, all right, generator breaker closed when all those conditions are met. So again, just a little bit of background there. One of the cool things we talk about in the power world is this idea of Ohm's law. Maybe you've heard it before. What Ohm's law does, Ohm's law gives us a way to relate resistance, voltage, and current. Those three things are really critical for us. We have those same basic parameters if we go the magnetic side of the house, but we'll just keep it simple today and just talk on the electrical side. Now, a lot of you probably dealt with this before, or at least have heard of it. One of our key things is when it comes to resistance, resistance is just like the term implies. It's not something any of us really like, and the same thing in the electrical world. It's typically not a good thing. Resistance, in what we talk about here, really turns out to be a loss. It's an inefficiency. So what we try to do is minimize any losses in our systems. So we had this idea of saying, hey, look, if I can control my voltage and I can control my current, I can minimize the effects of my resistance, or at least I'll design my cables and other such things to make sure that I don't have, or I will minimize my losses. That's particularly true when I get out to the transmission system. We'll talk about that a bit more when I get talking about the step-up transformers which has a very unique way of increasing voltage while at the same time causing a decrease in current. But again, we'll chat about that in a bit. So let's go back to a bit more of a detailed view. This is looking at just the unit itself. And when I say the unit, I'm talking about, we have the turbine here at the bottom. Oop, I need to get my little red ball back in play. It's so nice. There we go. All right. Well, say again, here's our penstock. We talked about that earlier. That's where my water's coming in. That water's coming in. It comes around here. You can see my little stay vane right here. This is where my water's coming around, all around the unit. And it gets smaller and smaller and smaller. Notice the size here, and over here it's much smaller. That again keeps a constant pressure of water being applied to my turbine, which is behind these wicket gates. It's the governor that controls the position of these wicket gates. These wicket gates all operate in tandem. That may actually tandem, may not be the word, they're in unison. There are several of these things, and they're all connected via, we don't have a servo motor, you really can't see. The servo motor is what connects up to the governor. The servo motor, it operates in truly in tandem. It goes in open and closed fashion. Those servos are working to position the wicket gates at any particular position along the way. So they can go be fully open to fully closed. Typically, hydro plants are not variably loaded devices. Either we pretty much load them up to their optimum point, or we keep them off. You know, and that goes back to something Jose mentioned earlier. Hey, if you go and operate your unit outside its normal bands of operation and you're just treating it not the best that you should, that creates a lot of wear and tear. So, as I'm saying here, we have our governor then is controlling the position of these wicket gates. As those wicket gates are opened up more and more, again, have a shaft that connects the turbine up to the rotor. That's what we're showing right here now, this rotating device. It's spinning in circles, just like the turbine is below. And then you can see this right on the edge. I'll go to the very edge side of it. This is where my stator winding is, which I'm just showing it here. It wraps completely around my rotor. So that's what we're going to talk about for the next few minutes, really focusing on my rotor, the stator, the excitation system, and ultimately the governor, which controls position of the gates. Well, like I said, we could start throwing out Maxwell's equations and start talking about Faraday's. We can talk about, gradients and curls for those of you that remember that from your days in engineering school. We're not going to do that. The
Jay,
great thing
sorry to interrupt, Jay. We have a question, which, the person says this could be for module 2, but I think this is a good spot too.
Yeah.
What's a typical operating range in terms of nameplate capacity? i.e. 40 to 100%, 75 to 95? That is the question.
Yeah, a good question. We designed these to operate at the upper end of their operational range. And I'm not putting an exact percentage on that, but they are, how shall I say, Jose, full load is where they typically want to be operated at. So that range, it stays at the very high end. You're not down operating these things at 10 or 15, 20%. You're moving through those zones really rapidly to get up to the not, and when I say the full range, let's just say it has a range from 0 to 100. You're never going to operate, you quickly go from that no load, 0, to start getting 60, 70, 80% load on these units. Once you get in at 80 to 90%, and you might have a 10% band at the high end. But Jose, obviously you have experience here too, so feel free to chime in.
Sorry, I was looking for the mute button. No, that's right, Jay. They typically are much more comfortable in the upper range. It also depends on the turbine type, as you know. Some don't like to be. You mentioned it earlier. Your propeller-like turbines can be more flexible. They can have a much broader range where they are comfortable versus your Francis turbines, which tend to behave better on the upper end as well. Cavitation, another reason. So.
Does that answer our question from whomever answered it? I hope it's not an exact number, but it gives you an idea, I hope.
Yeah,
We
that's
have
helpful.
great, and that was from Julian. We have another question, hands up from Kyle.
Yeah, hey, could you talk about like hydraulic short circuiting and ternary units in this as it refers to kind of this diagram that you have up? Thank you.
Yeah, great question. Where we're seeing ternary units nowadays, and just this so everybody understands, where I have seen them, they may be in other areas, but we're looking at ternary units typically at the newer pump storage plant designs. And really, what we're looking at is a way to have super fast control. You would have a short circuit, a true, as I think was Kyle shared, we would have a flow path that would basically come out of the discharge of a unit and allow it to go back into the suction of that same unit. That's one way we're doing it. Now, with some of the ternary units, the ternary designs, they are doing completely separate turbines and generators. That really gets, I think, quite hydraulically complicated and economically complicated also. And that's the thing with even with the ternary units, it just gives us a way to bypass a little bit of that water, or it could be all that water, so the unit could sit there in a standby mode and ready to go at a moment's notice to pump or gin, because it's not sitting there in an idle status, or it doesn't have to go through a complete shutdown before it can transition from a pump to a generator. Does that help at all?
Yes. So my understanding too is that you use a ternary unit so that you can operate your hydropower unit at its maximum efficiency capacity. But if the grid doesn't need all of that capacity, then you can reduce the amount you're sending to the grid by pumping back into the upstream. Is that correct? So if you're creating 50 megawatts, grid only needs 25. You can run a pump for 25 to pump your water back up. Is that another situation in which you use ternary, or is it mostly just this almost instantaneous reaction to the grid?
Yeah, it's more what you're saying there at the end. It just gets us to that instantaneous reaction. It allows to very, very rapidly control what's going on the unit. Because typically, like for a lot of our traditional pump storage plants, we have to completely turn them off. Take them, if they're pumping, we have to go clear back down to zero and go and then bring them back online. If you have a ternary unit, you are hydraulically taking it through those 0 points just by making the water go out in the pump direction up the hill, or allowing it to go truly on out to your lower reservoir into that gen mode. And a lot of it has to do, again, it's very hydraulic. There's nothing electric per se, except you're using the electricity obviously to run that unit.
Thank you.
Sure. Yeah, so as I was just starting to get us going here, talking about Maxwell's equation, this is what's really allows us, and where Maxwell and Faraday, some of the cool things that they started, and again, it's, we're talking 135 years ago, 150 years ago, they started coming up with it and realized they were looking at electricity, but they were looking at magnetics at the same time. And they started realizing there was this deep correlation between a magnetic field and current flow. And then they would also realize that, wait a minute, there's also, as I have an electric field, I'm actually creating a greater difference of potential. And so they started seeing this idea of magnetic fields having an impact on what's going on electric generation. So that's what a lot of the equations here, like I say, we're talking about taking the divergence, taking curls of these different things, and ultimately you end up seeing we have a relationship between magnetics and electricity, and magnetics and current flow. That's some, again, very basics, but some of the cool things that allowed us to get to the point of having motors and generators. Once they realized that you had this motor that or a generator could be created, and the impact it would have on the generation of current and voltage based on a varying magnetic field and that relative motion between it. Another key thing for us to focus on is the speed of our units. And I talked about this a little bit earlier. You know, a key thing when they design a unit, they're going to come up with this speed of which we want it to operate at. But realize too, frequency is a key item for us. Frequency is pretty much fixed here in the US, right? It's going to be 60 hertz. This other variable deals with the number of poles. So the designers, they're looking at these two values right here. This 120, kind of a fixed constant, but they look at the number of poles. That deals with the size of the rotor. The rotor has these poles associated with it. I got a diagram here in a second that starts letting us see what that is. These poles, what we're talking about is magnetic poles, right? We've been talking about we need this magnetics to create our electricity. That's how we get this idea of the number of poles. So what we end up getting is we have that water flow that's coming in that establishes our speed. Well, that's one item. And then we have number of poles, but ultimately what's driving this is, look, we got to create a certain frequency. So when I look about poles, well, here is a very simple machine. It has my A phase, my B phase, and my C phase. This outside would represent my stator winding. Inside of now this rotating device, that is my rotor. It's going around in circles, obviously in this A, B, and C fashion. Now, obviously you can realize if I have a larger generator, I have more and more poles on my rotor. This right here is a simple single pole device. This is a north and a south pole. That's it. My rotor will have several of these, 60, 70, 80 poles in the hydro space. It's interesting. That's in the hydro space because we're rotating pretty slowly. Hydro units, typical conventional hydro units, less than 100 RPM. Well, if you're less than 100 RPM, that is your speed. Well, frequency is established at 60 hertz. You can quickly figure out how many poles you're going to have. And so this is just when we talk about the poles, when we talk about generation of electricity, my ABC phase, this is what we're showing you. This is actually what's coming out of my generator, ultimately getting tied on out to the grid. And really what's driving it is obviously my rotor and my stator. Another key piece of it is the excitation system. We talked earlier about the governor being used to control the speed of the unit, ultimately controlling the number of megawatts that the unit is able to supply to the system. Well, the same thing, we have this idea of the excitation system. It's used to control the voltage. The voltage then, what it controls is the kilovolt amperes, my kVRA, my reactive power. This reactive power, so we have real power, watts, and we have imaginary power, reactive power. This reactive power, it's that energy that's stored in stuff. A motor, it has a magnetic field created in it. That magnetic field in and of itself is not doing anything, but something had to create it. That was the idea of why we need voltage. I need voltage to force those electrons along through my system. Hydro plants are really cool, and I wish I had more time to talk about synchronous converters and synchronous condensing, but it gets to a way that we can actually have minimal watts on our units and basically running them as a motor, and I can supply a lot of VARs to the system. You might hear it as VAR control, getting that voltage stability. It's one thing that really causes a lot of issues on the grid is voltage control. And so that's what my excitation system allows me to do. And different types of excitation system. We get these static excitation systems. Those are pure electronic, wonderful devices. And then we get brushless exciters. The older systems, we actually had rotating exciters. Hey, they worked like a champ for years, and there's a lot of plants that still have those. But again, just trying to say the idea excitation system, that's voltage control in our plants. Well, hey, got to do those knowledge checks to keep people in line. So, how is real power watts controlled on a hydropower unit? Giving you a chance to think about it. Again, real power, watts, how do we control that?
Folks are responding, giving them a few seconds. We got 2 so far. All right, we're getting some convergence here. The governor.
Exactly. And if I were to ask you about voltage control, I've asked you about the um, imaginary power, of course, you would tell me that would be my excitation system controlling my VARs. So the governor, via the wicket gates, controls watts, real power. And the excitation system, it controls my voltage, which in turn controls the VAR load. Well, the next big piece of equipment I want to talk about is the circuit breakers, specifically generator circuit breakers. Think of this as a very large light switch. These things can carry thousands of amps. I think the largest I've seen is, well, now I go to Raccoon Mountain, you get some of those. At the bigger pump storage plants, at our more conventional plants, these are, 1, 2, maybe 3,000 amps on the high end coming out of our traditional units. These things, again, they're what connect our generator to the transmission system. They are typically on the low side of your step-up transformer. They're between the generator and your step-up transformer. They have a lot of protective functions associated with them, i.e., we have our relays. Our relays are out there looking at currents, looking at voltage, making sure we're not overloading our units, and ultimately, because we don't want to damage things, right? And that's what an overcurrent condition could do, an under voltage condition could do that. There's lots of different things we protect for nowadays. But ultimately, when one of these situations arises that could cause damage to the equipment, we trip the generator breaker, we take it offline, the governor grabs a hold of it, keeps it from over speeding. The governor will drive the speed back down to get it to speed, no load, allows to get the plant into a safe condition. There's a lot of different pictures of generator breakers. I've got a few more on the next slide. I've got this right here would be a breaker out in a switch yard itself. You can talk about, generator circuit breaker. Like I said, lots of different styles. I'm going to click to another one here. Like inside your powerhouse, you might have, this is a little vacuum circuit breaker. It would go, a module like this would go inside the front of one of these devices right here. One of the big things we talk about is arc flash. Maybe you've heard that before. We want to do is that's pretty much this arc flash in the event that a failure, we want to contain all that inside of a housing like this. And it's these generator breakers, racking them out, removing them, installing them, a failure. This is lots of bus work inside of here. So we want to make sure that it's very safe. This right here, you got your, looks like isolated phase bus. This bus would go over to a generator, and then it would come out of the generator, out of this generator breaker, go on over to your step-up transformer. This device right here would typically, more than likely, have cables coming into this. You could have bus work come into it. I've seen that before too. But typically, this thing, like I'm saying, think of it as your big old light switch for the generator, and it has a lot of automatic features to turn it on and off, to get it paralleled. When I talked about the additive paralleling earlier, this is the breaker that would allow for that to occur. We'd be controlling the speed of my generator and the voltage of my generator to match the other side of this generator breaker, and then it would close it, and we could be going online making some power. So generator breakers, again, pretty cool devices. Well, this is a very simplistic view of a transformer. This is my core, we would call it. It have a primary side. It has, so many windings. I have a secondary side. It would have so many windings. And well, the cool thing about it is um, this number of windings. Again, you're connecting an AC signal, so you get this varying AC signal. You got some coils wrapped around a coil, this big old block of most likely copper, maybe, and so I've got some magnetic fields that are being created here. This is electrically, these are not connected. This load over here is not connected here, but we are through this transformer. I'm magnetically coupled to it. So what ends up happening with a transformer, if we have a voltage one and current one on what we're calling the primary side, well, we also have a current and a voltage on what would be the secondary side. If these turns are exactly the same, the primary and the secondary windings, this N number, if those were exactly the same, this would be nothing more than what we call an isolation transformer. The current and the voltages would be exactly the same. The turns would be exactly the same. There'd be no change in anything except it would just isolate the load from this power source. Well, what we end up doing at the power plants, we're going to have this ratio. We are going to make it so my primary side will step up the voltage, and then we're going to have a much lower voltage on what would be my secondary side. So again, it just what we're trying to do is we want to make sure this load we're going to call is like the grid. Our idea, our purpose is to get the voltage on the grid as high as I can. Because realize we get that conservation of energy thing going. Voltage times current is always going to equal power. So if I have one voltage go really up and I lower that current is going to go down just as I go through this transformer action, through those windings. So what we end up doing is we use this windings ratio to our advantage. We step up the voltage. And I'm going to go into my next little picture here. We have these very large step-up transformers. So what we do is we connect our generators to the low side, and on the high side, we connect the grid. From that, we step up the voltage that goes on out to the grid. We generate at 13,000 volts. We come out of these transformers at maybe 161,000 volts. Well, what that allowed me to do, by doing that, I have a very high voltage now going out to the grid. Well, at the same time, I'm able to lower my current. As that current goes down, I have less resistive losses. What we call it is I squared R. Power is equal to I. We square it. We multiply it by the resistance of my transmission line. So what we do is we get that voltage stepped up really high, and that lowers the current. Conservation of power on this transformer, right? The transformer doesn't make any energy. It just varies that current and the voltage. So we get the voltage up high, current down low, connect it to the grid, and my transmission lines have a lot less losses associated with them. So that's what the step-up transformer does for me. It changes the voltage to reduce my grid losses. A lot of times that transformer is out in my substation. It's a lot of times it's not inside the powerhouse. They will put them out here. We'll bring my cables out here now. Oh, I have lots of different overhead circuits, right? You've seen these substations before. Multiple lines will come to my powerhouse. I can send power off to all these different places. Maybe I'll have multiple units at a powerhouse. They'll all get tied together out here in my switch yard, allow me ultimately to connect up and send power and also receive power from other places at my facility. So that's what my switch yard is. A switch yard is just that. It's a bunch of switches, a bunch of breakers, a bunch of not only generator breakers, they can be line breakers. We also have current transformers right here, potential transformers right here. All those things apply back, go back into my control system for protective relaying, metering, and controlling of what's going on. Another key thing out in my switch yard is grounding. And this really comes back to safety. You know, we want to, everything is perfectly grounded to earth. And so we have incredible grounding systems out in our switch yards, going through our power plants. A lot of that goes down to just safety. We don't want to have step potentials, ground rise potentials, even the fence around these switch yards. We'll get those grounded so people don't get electrocuted when they come near our equipment. And yes, if it seems like I'm picking my speed up a little bit, I am. I am. There's a lot of good information here. Jose, you're going to have to tell me if somebody stretches that hand in air and wants me to slow down.
I think you're doing great, Jay. Thank you. It's a lot to digest. We did just get a question a few minutes ago, which I wanted you to finish that thought here. Can you please explain the terminology bus?
I'm sorry, I didn't quite hear the terminology. What?
The bus.
Oh, the bus.
Yes.
Sorry about that. Again, I'll start saying words and not explaining them. I apologize for that. The bus is it. You can think of it as a cable. A cable connects one thing to another. I'm going to go back here because I really love this. Where'd it go? I went too fast. I'm going to get there. Bear with me. Hope everybody's getting dizzy. Inside of here is a piece of copper. That piece, and it's inside there. It's braced really well. It's properly sized to carry all the current I want. And we refer to that as an electrical bus. The bus is it's a cable that takes the power from, say, in this case, the generator, which would be over here. And this bus carries it to the generator breaker. Inside the generator breaker, it's connected. And I'll flip the light switch on here, and it allows this bus to connect to this bus here to allow electricity to keep flowing. So yeah, the bus is nothing more than, think of it as a big old extension cable that moves electrons from one place to the next. Great question. I should have been more clear on that.
Yeah, thank you. Just wanted to piggyback off of that. Bus bar as well is a term that I hear often.
Yep.
And I assume it's very similar to there has something to do with the bus.
Yeah, exactly. A bus bar is nothing more than the piece of copper that we use to construct the bus. So we'll sometimes you'll say we'll disconnect the bus bar. Well, it is a piece of bus material that we can remove from a bus to open circuit it, and once it's back in place, it short circuits it. It's just a piece of the overall bus that I can remove for maybe maintenance, maybe, but it's just a piece of my bus.
Thank you.
All right. Yeah, we talked about grounding. Yeah, you guys get it. Go scoot your feet on long, shaggy carpet and touch your brother or sister on the ear, and you get what we mean by some of these issues that arise if you have systems that are not properly grounded. Well, unit protection and controls. Clearly, this is a big area for us. It's one thing if you have a generator, but if you don't control it, if you don't protect it, it's just such a major asset. And so, we have outstanding control systems, protection systems. This digital world has really transformed what we can do with our hydro plants. As far as you think, how many people we used to have at our power plants. You would have a governor operator, multiple people down there operating the governors, and people going over to operate your excitation systems. And, you have people in the control room, and there's an awful lot. Well, nowadays, most of our plants are unmanned. We don't have anybody at most of them. They are all remote control operated. TVA operates all their controls, all their hydro plants from Chattanooga. Raccoon Mountain is their only plant that has people there 24/7. It's just the sheer importance of it. You just wouldn't want that plant to go offline and somebody not be there to take care of it. But in the idea of controls, we talk a lot about, you'll hear terms SCADA, supervisor control and data acquisition systems. That's what SCADA stands for, RTU, remote terminal units. These are all just pieces and parts of how we monitor our control system. And the idea of dam safety, we're doing that too. We're looking at the positions of gates, looking at the positions of motors that control those gates. So an awful lot going on in this area. And again, it just allows us to remotely operate our plants and not have to have people out there. It allows for the very safe operation of them and highly efficient, right? You think about just not having to have people out there all the time. We have a lot of roving crews that transition. Maybe you have one crew that might have 3 or 4 plants that they go to over the course of a week. Then again, just to check on it, make sure everything's operating and safely, no problems have come up. Oh, there we go. Yeah, unit protection and controls. It's sort of separate from the governor excitation system. And I say it's separate, but yet highly ties into those systems. A lot of times these governors, it's just looking for an input. And so you want to increase or lower speed. But in and of itself, it's going to control itself. It's going to shut itself down. It has its own protection systems to protect the governor. The exciter, same thing. The exciter, it's looking for that external input to raise or lower voltage. But as far as its internal controls, it has all kinds of protective features associated inside of it. And governors, exciters, and these other control systems, they all tie back to other relays that ultimately open that generator circuit breaker. It's that generator circuit breaker that's the idea. That's what provides the isolation in the event of some problem internal or external to the system. It's looking in both directions to get the unit in a protected status, get it off the grid if the grid's going crazy, or if the generator's going crazy, to get the generator off the grid. Either way, it's looking at it with all kinds of things we're constantly looking at. We have control rooms. I got some pictures here in a few minutes. We'll look at those to show what they're looking at there. But you see those NASA control rooms with all those computers. That's what we have too. Lots of protective relaying. Again, it's just unbelievable. We have these multifunction relays, we call them. We used to have all these standalone, single phase relays that could only look at one phase at a time and only look at one thing at a time. You had one relay, and all it was doing was look at what current was going on A phase, or just B phase, or just C phase. And we had things where we're looking at just voltage, what's going on there. Well, nowadays we got these multifunction relays that they're able to look at all 3 phases. They're looking at all the currents, all the voltages, all the differentials in those phases themselves. That we talked about, that 120 degrees electrical separation. They're looking at that. They're looking at how rapidly current is changing, how rapidly voltage is changing. It's so many calculations. These things are just computers. It's all they are. But we're able to feed in very basic information, and these relays are, because they're operating so rapidly, before the fault even gets very far down the road, if you will, before it gets very aggressive, before it gets very large, these things already see where it's going. It's anticipating functions that's saying, hey, look, in the last fractions of a millisecond, the current went up, 3 amps. Well, you and I would say, well, 3 amps, that's nothing. But it did that in milliseconds. So it's able to say, hey, look, if this thing continues for 2 cycles, we're going to be so far over current. So it trips really early. It's just amazing. I could be a geek here for a minute. I'll stop. But we got my good friends at IEEE and ANSI. They're coming up with all these great numbers to figure out what's going on and to help us talk the same language. what we're looking at here is I talked about the idea of protective relay, and you can see a lot of these are older relays, same on these boards over here, but you can see some of our newer ones right here. As these newer ones are replacing a lot of this old stuff, I'm sure as you go out at your plants, you're going to see a bunch of blue relays. We got smaller little circuit breakers, bunch of little relays. All these things are working in unison to keep our plants very safe. This right here shows an operator looking at some of the computer that we are looking at through our data acquisition systems, allowing us to actually see what's going on at our plants. It's amazing the amount of information we're bringing into our control systems nowadays to actually see what's going on, protect the plants, operate the plants a lot better. When they operate, I'm also thinking about the maintenance side of it. We're able to do so much more trending. We can see exactly, hey, what's this bearing temperature at this megawatt loading at this time of day, and seeing exactly what's going on. We're looking at cooling water flows and just be able to see exactly, so we can be more predictive on our maintenance and operating the plants much more efficiently. Again, I talked about these earlier, the RTUs, it's just remote terminal units. They're just microprocessors about gathering lots of data, sending it back to our control systems so we can see what in fact going on. This would be a typical control room. And this would be a control room that's monitoring several plants, not just at a one hydro plant. No, this right here would be something like we have in downtown Chattanooga that's showing all 29 hydro plants being monitored, all 109 units they could be looking at, swapping between them, bringing units online, offline, looking at water flow, looking at storms that are coming this way, monitoring all kinds of stuff, and just maybe 1 to 2 people on every shift. So pretty amazing what we're doing nowadays. Again, I would love to talk about that a whole lot more, but time is our enemy at this point. I want to spend a few minutes talking about the balance of plant systems, particularly on the electrical side. Again, as you guys get into the mechanicals and other systems, they'll get a lot more into that. But just on the balance of plant electrical systems, like I talked about, we have DC systems, direct current systems, battery systems at the plants, and also we have our alternating current systems. We have lots of security systems, fire protection system, HVAC, heating, cooling, lightings, all kinds of stuff going on at these power plants that take internal power. These are loads that we have to, account for, loads we have to make sure are energized in the event of a failure. We need to make sure we have power available to keep all of our most important loads, the loads that are required for us to come back in a black start situation. And when I say black start situation, just to define that term a little bit, it's to say that if the grid goes completely dark and I become an island, if my hydro plant becomes an island, it's at that point I'm saying, look, I have no external power. I'm in the dark. So in that situation, can I start my plant up? And a vast majority of hydro plants can come back online in that scenario based on the fact that they have DC systems and they have a few AC systems. And some of these AC systems are being fed from the very large batteries that they keep on site. We have this idea of station service power, very large motor circuit breakers. We have things like you have in your house, controlling all of our lights, smaller loads. We have these automatic transfer systems that allow, in the event of a power outage, to swap from a normal source of power to a backup source of power. A lot of our plants, especially to make sure we meet all of our dam safety requirements, we have a lot of generators on site to make sure we can do that. A lot of smaller transformers to feed these loads. I talked to earlier, our DC systems are comprised of very large batteries we have there. We obviously have battery chargers there that are keeping those things in peak condition. Our technicians are constantly having to go out there making sure the batteries are in good shape. I had several projects over the course of my career of replacing old batteries at plants to make sure we had new batteries that were ready to supply the power when needed. Well, quick little summary on the electrical slide. We can take a breath for a minute, but we talk a lot about this idea of this hydropower basics, so the energy side and how we actually calculate it, just very simple, the I squared R. We go do some efficiencies of our plants, talked an awful lot about some of these basic components that we have. The electrical system is a key part of it, but also all these other little pieces and parts on the mechanical side, all ultimately get us from our turbines through our generators and get us to our transformers. Specifically to the electrical side, we're talking a lot about the protection equipment, our generator circuit breakers, our big light switches, our SCADA equipment to keep track of everything. A lot of this stuff is unmanned. There's no one out there, and we're relying on these computers to operate all of these plants. Well, I'm going to take a quick breath and say, any questions? Any comments on what we talked about the last hour or so? I appreciate a couple of people chiming in as we were going along, but any questions related to things we talked about over the last hour or so?
Yeah, Jay, undoubtedly a lot of information that you've shared, a lot of knowledge that you have not only garnered over your contributions and participation in this industry, but a lot of expertise just out of your background. And a reminder for folks as they may be thinking of questions, we are recording this, and this will be available for all of you to go back and use as a little bit of a Rolodex as these modules come together. So you can, in essence, look back and reflect on some of the topics that were discussed here. Some, of course, which are probably quite intuitive if you have that expertise, and some that are brand new. So there's been a lot of information that has been provided. So please take advantage of that. Jay, I'm not seeing any questions here or any hands up at the moment. And as a time check, it is 4:30.
Yes, I think we're almost on time. Yeah, thanks, Jose. And just to follow what Jose is saying, hey, it's not like Jose and I are disappearing after this class. This is a bit of a community. This is something NHA is doing. There's a lot of us that have been around for a while that just love to share our knowledge. And if there's questions that come up after the fact, the folks at NHA know how to get a hold of me. My email is pretty readily available. Feel free to reach out, ask questions. Not going to bother me at all. I appreciate hearing from you. Well, moving on. Our last topic of the day. And what we want to spend is just a few minutes just talking about a typical river system layout. Now, again, in here, we have one that's definitely a part of the module. What I've done to help me out, and I'm hoping to help you out too, is to focus on a river system I'm just very familiar with, right? I've lived here in Chattanooga for almost 30 years, ever since when I got out of the Navy, I moved here and started working with the Tennessee Valley Authority. So I'm just very familiar with their system and can explain some of the nuances of it. And then we'll go through another system where I'll maybe more rapidly look at that, but still showing how all these pieces and parts play together. And to look at a hydro plant in a very single way really is a disservice to hydropower, because it's such an interplaying system. The plants, the way they interact together, the way we plan them from the operations side, just trying to squeeze every electron out of that drop of water. So let's think about this, just a regulated river system. That's what I want to talk about. A regulated river system. We talk about it has this different things going on. It can have this combination of conventional plants, run-of-river plants, pump storage plants, big plants, small plants, all intertwined with that will be navigation of plants, and navigation of the river itself. So much of it plays in to it. And so we just wanted to give it thoughts. A lot of the stuff we talked about today, just hopefully pull a little bit of it together as we just go through a typical plant. So this is where I live. This is the Tennessee Valley Authorities, and particularly you see the two different colors. Well, the darker green, that is the drainage basin for the Tennessee River. So it's all this water here in these different areas, clear up to, well, West Virginia. All that water drains into and starts to be the confluence for our Tennessee River system. Tennessee River starts way, I should say Tennessee River. Our water starts way up here in the West Virginia area, over here in the mountains of western North Carolina, and ultimately that water's all draining, from over here, even in, Asheville, North Carolina, clear up here, Bristol, Virginia, for those of you familiar with it. Anyway, this right here, the Smoky Mountains are right in this area, right up here, so you can see we have, I was a little bit off mark right here. So we have all these different river systems all draining into the Tennessee River. Ultimately, the Tennessee River, it's flowing. And notice I talked earlier, it kind of just comes to a little piece of Alabama, go along Alabama and over a little bit into Mississippi, and then there we are on up through Kentucky, dumping it into the Ohio River, ultimately going out into the Mississippi River. What we show here, all the different dams, we got these little black lines, if you will. Those are representing all my hydropower plants that feed into the Tennessee River. You notice there's this one little dam over here. Kind of interesting the way stuff happens. That is the only dam on the TVA system that does not drain into the Tennessee River. It drains into the Cumberland River. The Cumberland River is managed by the Army Corps of Engineers. This one little plant right there, excuse me. Does anybody tell us what it is yet, Jose? It is
Nothing.
called Great Falls Hydro Plant. Back in my days of being a plant manager, that was one of my plants. I had that plant right there, and I had the Watts Bar plant. So again, these two are not close to each other at all. You can imagine. You look at there's quite a distance in there. And anyway, but that was my days of being the plant manager. Like I say, those two particular sites. I wanted to show this right here is kind of a cool, and I'm hoping it comes out. Oh, you can see it nicely. I'm looking at what's on my big TV screen. Hopefully you have this on a big TV screen and you can actually see it. What I wanted to start off, we come up here and we can actually see the different names. We got Norris Dam. It's interesting. Norris Dam, that is the first dam that TVA actually constructed, and it's named after the state senator of Nebraska, not Tennessee. Mr. Norris was big in the TVA Act, helped get the TVA Act enacted, and so the first dam that TVA built, they named after him. I always thought that was interesting, but it wasn't one of our own state senators. But now I talked earlier about the Cherokee and Douglas, these two plants over here, very, very similar. I mean, and you can almost look at the plants, the way the river necks down in front of them and behind them. There's a lot of similarities on those two particular sites. We go up in here and you can kind of see this obviously being the start of the Tennessee River, but we have the Holston River that comes out of up here in the Virginia area. And then, of course, we have our other, this right here is Asheville, right over in this area. This is the North Carolina border. You can see that. That's where we get this water coming out of Asheville that actually feeds into the Douglas Dam. All these are what we consider main river dams. These are all very large dams. All these, Kentucky, Pickwick. I talked to you earlier about Wilson, Wheeler, Guntersville, all those ones down in North Alabama. Nickajack, Chickamauga, Watts Bar, all these are very traditional peaking plants. Now, when I get into some of these ones off the main stem, this is the Ocoee River over here. These are all run of rivers. Ocoee number 1 has a little bit of a reservoir behind it. It's not necessarily a run of river, but Ocoee number 2, Ocoee number 3, Blue Ridge, Notley, Chatoog, those ones over here in the middle of nowhere, those are all ones that are what we call run of river. Ocoee number 2, what's really unique about Ocoee number 2, for those of you that have driven along the river there, it still has a wood flume. You think about those old wooden flumes, maybe those of you in Ohio went to Kings Island or something, you get in those log flumes and you splash everybody else. Well, that's the idea of here. We have an old wooden flume right along the line that comes from Ocoee number 3 that ultimately feeds into the Ocoee number 2's powerhouse with a penstock that goes up the side of the mountain. It's here at Ocoee number 2, some of the best whitewater rafting in America. And I say that I think it's fair because the Olympics was held here, back in 1996, we'll say. And I think it's close. Anyway, we had the Olympics held here. It was downstream of Ocoee number 3, between Ocoee number 3 and Ocoee number 2. That's where they had the Olympics. They went in. It was already a great whitewatering spot, but they went in because it was the Olympics. They did some man-made manipulation. Really is quite cool. So if you're a big whitewater person, I definitely highly recommend you come and do some whitewater rafting right here. Hiawassee. It's our other one over here. It's on the Hiawassee River, of course. That's how it gets its name. But this idea we have Hiawassee is here. It's a very large hydro plant. It's a lot of, you can look at the drainage basin. It has 2 very large rivers. But then this Appalachia Dam, well, we talked about dams that maybe have penstocks feeding them. Well, Appalachia Dam is here, but the powerhouse is way downriver. It's several miles downriver. We've actually got a buried penstock that brings that water down to there. I share all this to say we got all these different types of power plants, but a lot of our water, the water happens over here in the mountains where a lot of these smaller sites are. That's why Douglas, Cherokee, Norris have very, very large reservoirs. But then we control the release out of these reservoirs. So as we're getting the power, getting that water to these various dams downstream. So it's really, even in the summer when it's dry as ever, we're going to be releasing water out of these very large reservoirs upstream. Well, you can see if I'm letting water out of these places, and again, I told you, they have a huge reservoir at these tributary dams, we call them, because they're on the tributary rivers to the main river. Well, again, to get them all operating together. And what's really cool, we used to have a lot of coal plants. Now, again, hey, coal's not cool, I get it. But there was a time we had a bunch of coal plants, and we still have our nuclear plants. They're all along the main river. Well, they needed cold water at certain times. So what we would do, especially out of Norris could really send out some cold water. It's a very, very a deep dam. Well, Fontana was the same way. I want to find Fontana on here. I think here it is, Fontana. Another one, very high head dam. Well, if we want some of that cold water out of these high dam places, because I maybe have a big old coal plant down here, we would, at certain times of day, we would schedule a great deal of release out of this hydro plant to make sure that this fossil plant down here would have that slug of cold water when they needed it so it could run much more efficiently. I say that just to share. It's the way that we're managing these rivers. We have all these different types of hydro plants, different types, and then different ways, different amounts of reservoirs. We got all these running rivers down here that I really can't do much. So I have to say, hey, look, I know here at Chickamauga, it's going to get all this water if there's a big rainstorm coming out of the Ocoee rivers and out of the Hiawassees. So I might hold back here at Watts Bar and say, hey, Watts Bar, we're having a storm over here in the mountains. You curtail your generation right now because Chickamauga is going to get all this water from these tributaries over here. So we'll let that water come in. Chickamauga will generate a whole bunch, send its water on down through the system. Watts Bar will store for a little while. Once this slug of water gets through, Watts Bar can get back to its generating, supplying all those downstream plants. So again, I just share that, see the way it's just all so heavily integrated, and all the thought. And there's a whole group of people that sit up there in Knoxville, Tennessee, looking at their computers, figuring out when it's raining here, who needs water there, and to make sure we efficiently operate all these hydro plants. Not to mention, right here, we got a big old pump storage plant that's sucking water out of the Nickajack Reservoir on and off all day long to provide that really great grid support. So again, like I say, I just specifically go over the TVA only because it's one I'm really familiar with, and it shows how a very large integrated system, like the 29 different hydropower plants, one pump storage plant here, whole bunch. If I go back to that previous drawing, you got all these thermal plants, whether it be down here, these are all nuke plants down in this region. We have, well, actually, it's a nuke plant. We have several nuke plants. We have Watts Bar, and we have, of course, right outside of Chattanooga, we have Sequoia, Bellefonte here in North Alabama. So a lot of nuke power going. Actually, Bellefonte's right here. Sorry, this was an old coal plant, Widows Creek. It is no more. Anyway, that's just a real quick look at a river system. Another one we have here, and I'll take a couple minutes. It's just looking at the Deerfield system. You look at this one, sort of on the border of Vermont and Massachusetts, and you can start seeing, on the Deerfield River, it too, much like TVA, several different hydro plants. Now, these are all much smaller. Most of the ones I've shown on the TVA main river, most of those are anywhere from 150 to 200 megawatts for each plant. These are here much smaller ones, but even though they're smaller, they're still very integrated. They're still all working together as far as providing storage, re-regulation. We have ravines the water is going through. They have storage projects. You have run-of-river projects, and they're working those all together to again, get the most they can out of it. This particular system, 10 different hydro plants. They're realizing the penstock, like I was talking about. They have power canals, also tunnels, like I was talking with Appalachia and Ocoee. The integrated, some powerhouses right into the dam. Then they have some storage requirements also. So again, very, very integrated, and they'll have one place operating the whole thing. Now, again, they're talking about their storage of where that was. I think these are cool. Called a glory hole. This is a way, once the water gets up to a certain elevation, this is what gives us a way to spill that water to maintain the elevation of the water in this and not allow it to go anymore. Very much like a spillway. But in their system up there, they talk a lot about the way they're using it to the controls to control the reservoirs, looking at the dams themselves. This right here, they've broken down these next several slides, looking at some of the individual plants. I'm not going to get into that, but you can kind of see as you're looking at them and realizing what they're doing. When we talk about re-regulation, they have a lot of running rivers. Well, what they would do, maybe they'll feed all several of those run of rivers into one re-regulating place, or essentially it's a place that has a reservoir to give a chance to collect all of that flow from several run of rivers. Say, okay, let's at least give ourselves a little bit of regulation through all those run of rivers. Now, again, down here we have the Ocoee #1 reservoir. Couldn't look like a re-regulator, but on the output of it, it goes into the Ocoee River, which ultimately feeds into the Hiawassee, which ultimately feeds into the Tennessee River. And yeah, it just that allows us to regulate it really, really well. But sometimes if you have a lot of smaller plants, you'll incorporate some re-regulating ponds or reservoirs to help you out there. This one just showing us how we're got the dams and the powerhouse kind of integral to one another. Again, very old facilities, but really cool looking at the infrastructure there. I really, really do dig that. Yeah, it's very actually showing us the powerhouse. It's amazing the similarity in these powerhouses of the era. Just the craftsmanship. A lot of the Ocoee plants are this same way. A lot of brick craftsmanship and everything, and concrete. And these guys really did just some amazing work. Now, again, the things they point out in their ravine generation station, it has this bypass reach that comes to it. And I really want to look at that. I think the next slide does. Okay, if I can grab my little mouse to come and work with me, I don't know, it's getting tired here at the end of the day. I'll get my finger to do it for me. Boop. There we go. Yeah, so this one they have what they call this bypass reach. This is the way of you're bringing the water there in a penstock, but ultimately too there's this long section of the river where we would pass water if in fact we had it. Boy, my little guy here is not happy at all. Yeah, I'll do it the old-fashioned way. Maybe I will. Well, yeah, again, just want to go another picture here. You can see the bypass reach here. And what I like about showing this, you can really see how the bypass reach has minimal water going through it. And then of course they're showing the where the powerhouse is and how they're having the penstock sort of embedded in the ground there, coming down to the powerhouse. They have their water which they pass underneath the penstock to that forebay area. Again, we have this is very much like Ocoee number 2, and that's why I say you could see that where the bypass region is right now. If that was really long, if you were to really flood that would be quite a little whitewater ride you could have through there. Obviously, you wouldn't be generating at that time, but you can see kind of what we do through some of the bypass regions. And so here's another view of where they have the bypass, where you can see where they're in the yellow dashed line, where actually the power canal is, how we get the water down to the powerhouse, or the bypass reach when they are not generating, or they look like it's the minimum flow requirements here. You can see how it's overflowing the dam going down to it. And they also, even though it's a very small place, they have Bear Swamp as their pump storage facility. You can see kind of the lower reservoir, the river system that they are using. They have a bit of a dam there to give them that lower reservoir, and obviously the upper reservoir topography is kind of tough. You can't really see it all that well there, but showing how that water is in fact being impounded there, and then the powerhouse sort of down below. Well, one last knowledge check here. What is the difference between a storage project and a river re-regulating project? Storage vice re-regulating. I'll let you guys think about that. This takes a lot of words, and so maybe in the sense of not having to type an awful lot, I'll just go put that up there. But a storage project, it really are reservoirs there, right? The water can be stored until it's needed. It's very much used for our peaking facilities. Vice re-regulating, it absorbs that, releases from the upstream projects, and just gives us the ability to re-regulate that flow, to send it out in a more controlled fashion. One other question for you, make it real simple, true and false. Can an open loop pump storage project use the impoundment of a conventional hydroelectric project as its lower reservoir? I'll give you guys 5 seconds to type, but
they're coming in. They're coming in. So let's give folks a little bit. We have a couple of responses, Jay.
Sure.
One is a confident yes. The other one is a maybe yes. So, but most of them are yeses.
Okay. Well, the yeses have it for sure. That's definitely true. And the key word there is open loop. Obviously, if that would have been closed loop, well, we would expect a different answer. Again, just a couple last thoughts here on their plant. And again, it goes back to another, again, talking about they have their 10 different plants, over 65 miles of reach on the again, just to give a matter of scale. And I love the scale here, by the way. This is a 65-mile reach. Bonus points to whoever can tell me how long the Tennessee Valley's river reach is on the Tennessee River. Any takers?
We got one so far.
Okay.
Let's see if we get another really quick. The first guess by Wesley is 250 miles. No other responses so far, Jay.
They're thinking about it.
You should give them a, it's at the end of the day. Are they cold? Are they warm? Are they hot? Maybe that'll trigger others to respond.
Yeah, it's and again, if you'd picked up on my fact that I said I really love this scale, it's this river system is 65 miles. The Tennessee River is 652 miles. And I love the number 652, by the way, because that was my submarine's hull number. It's one of those numbers I look at a digital clock and I forever see that number. It's one that's just kind of embedded in my brain. But yeah, so a scale of 10 times that for the TVA River, but yet it still very much has a lot of the same stuff as small scale or large scale. And again, they just gave us a few more specifics on some of the plants. And and you get it. Look at the size of these plants, 4 megawatts, 17. Bear Swamp, serious, 600 megawatt. That's a nice size pump storage plant. And some of the other plants, again, 10, 4. Yeah, pretty small ones. Well, wanted to wrap up this section. We just talked about a typical river system layout. It's going to contain all kinds of different type of power plants, operate in different modes, different regimes. You can have your conventional, you can have your, storage. You can have no storage. You can have all run of river. You can have peaking. You can have pump storage plants. You can interface with a bunch of your thermal plants, interfacing with, your navigation systems. So an awful lot going on. And why I say interfaces with navigations, because in high flow conditions, navigation is greatly impacted, and we in the hydro space have to be cognizant of that. Well, with that, congratulations, you have finished our first full day module. I appreciate you guys being here. Let me be a part of this time with you all.
Excellent. Well, Jay, thank
Thank you,
you.
Jay.
And I know we have a few minutes for questions. I just wanted to let's do a quick open mic session. If there are any, I have a few closing things, and I want to thank Jay in a moment. But let's see, is there any open mic questions that folks have or comments?
I'll put this on my big screen so I can see you guys.
Well, I'm not hearing any. Maybe we'll get one in a minute or two. But Jay, first and foremost, thank you. You have given us as a team and to the class an incredible amount of information. You started out slow, and you certainly picked up the pace as you really got in stride into all of the different things that one should consider, from the mechanical to the electrical to how water has to be managed. So you covered a lot of ground for the folks on the call. Thank you for hanging in. I think most, if not all of you, hung in from the beginning to the end. I know that you're part of this course and you're paying for it, but I really appreciate everybody hanging in there. As a reminder, our next class will be on December 18th, so make sure that is on your calendar for module number 2. And also as a reminder, there's a lot of material, great material here covered. Take advantage of that. Go back to look at the video so you can compare your notes. Be sure to complete your knowledge checks. And again, we are here as resources